Okay, today we're going to review chapters 5, 6, 7, and 8 for test 2. Here we have a problem. We're just going to get right into it. 150 gram ball at the end of a string is revolving uniformly in a horizontal circle of radius 0.6 meters. The ball makes 2 revolutions per second. What is the centripetal acceleration of the ball? And what is the centripetal force on the ball? So I will start by doing the first example here just to get everybody warmed up. And then as we go to the next several examples that we have here, I can give you guys some time to work on those problems. Okay, so we have a ball on the end of a string, looks something like this, and it's revolving uniformly in a horizontal circle of radius 0.6 meters. Ball has a mass of 0.15 kilograms or 0.150 kilograms, just converting grams to kilograms there. If the ball makes 2 revolutions per second, that's telling us something about how fast the ball is moving. So it's going around this circle 2 times per second. Well, how much distance does it cover in 1 second if it travels around the circle 2 times in 1 second? Well, the distance around the circle is given by the circle's circumference, 2 pi times the radius. But it's going around that circle twice, so we should multiply by a factor of 2 there to get the total distance. And that distance is traveled in 1 second, hence 2 revolutions per second. And so that would also correspond to the speed of the object. And so we'll go ahead and use another color here. So the velocity then would be equal to the distance divided by delta t, and delta t is 1 second. So let's go ahead and you guys can calculate along with me. Get out your calculators. And we just want to calculate the speed of this thing. Once we have the speed, then we're ready to answer the question, what is the centripetal acceleration? Because centripetal acceleration is given as the speed squared divided by the radius of that circular motion. And so once we have the speed, we can square that and divide by the radius that was given, and we'll have the centripetal acceleration. So okay, hopefully you guys have your calculators out now. So we're calculating d first probably, so 2 times pi times 0.6, and then times another factor of 2 there. So the distance traveled around the circle is equal to, let me get the red, 7.54 meters, keeping 3 sig figs, because 3 sig figs is the smallest amount that's given in the problem statement here. So 7.54 meters traveled, but it's the same, that same distance is traveled in 1 second here. So when we calculate the velocity, it's 7.54 meters divided by a delta t of 1 second, which gives us 7.54 meters per second. And so there's our velocity there, and that's going to need to be plugged in right there. Okay, so now calculating the centripetal acceleration, 7.54 meters per second squared. That's the square of that entire quantity there, divided by the 0.6, let's get the units there, 0.6 meters. And we come out with an answer. Again, let's go ahead and go over to the calculator here. I can take my answer from the last calculation, I can square it, save a little bit of time calculating since we are studying for a test here, so we don't want time to be a factor. So take that answer you got last time and square it, divide by 0.6 meters, and what we get here is 94.7 meters per second squared. And now whenever you get a big acceleration like this, you should probably always ask yourself if that makes sense. Well, we look at our velocity here, and our velocity is pretty big, 7.54 meters per second. And the radius is about half a meter, so maybe like 1.5 feet. So this thing is really traveling fast, considering the size of that circle that it's moving around in. And so this really large centripetal acceleration is pretty typical for those kinds of motions because it goes like v squared. So this answer does in fact make some sense because of the large velocity that we have here. The next part of the question asks us to calculate the centripetal force. Well, the centripetal force is simply the mass times the centripetal acceleration. So that part is just a straightforward application of Newton's second law. So if we want to calculate this, the mass, we don't want to plug in 150 grams, we want to convert that to kilograms, so 0.15 kilograms. And then we're going to multiply that by the centripetal acceleration there that we calculated, and that's the 94.7 meters per second squared. And what we end up with in the end, again, we can go ahead and take that last answer we got in our calculator and just multiply that by the mass. Again, we want to practice saving some time in our calculator here for our calculations. So I take my answer from the last part and I multiply that by 0.15. And what I end up with is 14.2, keeping 3 significant figures. The units of force, kilogram meter per second squared, is the same as Newton's. And there we go. That completes parts A and B here for this example. Let's go ahead and recap what we needed to do there. So we have a ball on a string. It's uniform circular motion. They tell us the number of revolutions per second. So if we know the number of revolutions per second, then we need to convert revolutions to an actual number of meters that this thing travels per second. And so that's what we did right here in red over here to get the distance. 2 revolutions means going around the circle twice, so 2 times the circumference of the circle. Then in blue down here at the bottom, we took a delta t of 1 second because it's revolutions per second and use that to calculate the velocity. So it's the same 7.54, but now it has units of meters per second. Then we apply our formula for the centripetal acceleration here, which is v squared over r, the radius of that circular motion. And we come out with this 94.7 meters per second squared here. Then that completes part A. Part B, mass times centripetal acceleration gives you the centripetal force. So we simply take that answer from part A and multiply by the mass of the ball, given as 150 grams, but make sure you convert that to 0.15 kilograms. We end up with 14.2 newtons at the bottom there. So does anybody have any questions with regards to this example? Or are we ready to move on to the next example? Ju, are you good? Oh, I missed the chat. Okay, cool. So we'll go on to the next one, and I'll let you guys work on this one, or you gals. The two of you can work on it together if you want, or if you want to work individually. What do you two want to do here? And of course, I can get things started if you need me to get things started on the question. Let me go ahead and read it so we know where we stand on it. So the next example, a 0.15 kilogram ball on the end of a 1.1 meter long cord is swung in a vertical circle this time. So it's a vertical circle. And we can see over here we have a diagram of what's going on here in this problem. So since it's a vertical circle, we have both the gravitational force and the tension in the string to deal with. In the previous example, where we have a horizontal circle like this, the only thing that we're really dealing with here is a centripetal force, which is due to the tension in the string. But there's only one force, so it's kind of easy to manage. Over here, things are slightly more difficult, but not too much more difficult. Because when we read part A here, it says, determine the minimum speed of the ball at the top so that it continues moving in a circle. And so when we're looking for the minimum speed, that means when we're at the top, that the gravitational force, mg, will be equal to the centripetal force. So we'll put the minimum speed here. Okay. So why don't the two of you work on this one for a little bit, and we'll just stay as we are here. Just let me know if there's a question. And then if you have a question, just you can say something in chat, or if you get an answer, maybe put your answer in chat so that way we can compare answers. I'll go ahead and reiterate here that since the centripetal force is only mg, then that means that the tension force, which is labeled as Ft1 at the top of the circle, would be equal to 0. Just to make sure it's crystal clear there.
Wait, sorry, can you repeat what you just said?
Yeah, so when we're looking for the minimum speed, the centripetal force is only due to the gravitational force at the top, which means that the tension force would be equal to 0.
Oh, okay, yeah.
If the tension is bigger than 0, then that would mean the speed is larger, so it wouldn't be a minimum speed. Does that make sense?
Sorry, I started calculating. Can you say the last part again? I'm so sorry.
Yeah, sure. If the tension force is bigger than 0, then the speed will be larger.
Oh, yeah, okay.
Right. So
Yeah.
bigger centripetal force would mean bigger speed, so that wouldn't be the minimum speed.
I got 3.28. But actually, let me check my work really quick.
Okay, and you can put your answer in chat with units. How are you doing, Ju? Do you know kind of what you're doing here for this one? Okay, Christine has 3.3 meters per second. Go ahead and start working on part B if you know what you're doing. Okay, Ju, let me get you going here on this problem then. So let me kind of like talk you through it and hopefully like get you warmed up here. So if we're looking to calculate the minimum speed, well then we're at the top of the circle here, and the force that's driving the circular motion is the centripetal force, right? But since this is a ball on a string, there's a tension force and there's a gravitational force, right? So the net force is going to be equal to the centripetal force, and that's going to be equal to the force due to gravity plus the tension force. It's labeled FT1 in the diagram at the top right, so I'm going to use the same notation there. This tension force should be equal to 0 if we're looking for the minimum speed. If you put a ball on a string and spin it around your head, like above your head, if you want to spin it faster, you have to pull on it harder, right? So the bigger the force, the bigger the speed. So if we're looking for a minimum speed, you can see it in pink up here. If we're looking for the minimum speed, then we want the force to be as small as possible, but we still want it to be in circular motion. So we're going to set the tension force equal to 0. We can never set the gravitational force equal to 0, right? The gravitational force is just always going to be there. And so what we get from that is that the centripetal force is equal to the weight, or the gravitational force is equal to mg for this ball. But since it's a centripetal force, it's always equal to mass times v squared over r, right? Centripetal force is always mass times centripetal acceleration. If you want, let's go ahead and make it so there's one more step here. We'll go ahead and we'll say, well, centripetal force is equal to mass times centripetal acceleration, which is equal to mass times v squared over r. Masses are always going to cancel out, right? So what we end up with is g equals v squared over r. And we want to solve this for v, right? Solve that for v. So how would we solve that for v? I know that was probably like a long way of going through. So let me know, like, does that make sense? Does that process, like, does the logic make sense there? Okay, good. So once you solve for v, that is the minimum velocity. Yeah, you're welcome. Let me grab a glass of water. So Jude, do you have the velocity now? Ah, okay. Christine, do you have an answer for part B yet?
I'm on the last step. I just need to finish my calculation for FT and then add the or subtract. I need a second.
Okay, yeah. I am going to go ahead and calculate the min velocity here, just so that way we can all check our answers. Okay, and I have the following answer here: 3.28 meters per second. So I think, Christine, you got that, and then
Oh,
Jude,
yeah.
still waiting on you. Let's see if you can get that.
I just did the wrong sig figs for that. I thought it was two sig figs.
Should be 3 because it's 3
Yeah.
given for both. Yeah.
Yeah,
Yeah.
I don't
So,
know why I thought it was two. It's definitely three, yeah.
yeah. Well, on the test though, like, usually the answers like A, B, C, D, right? They all have the right number of sig figs, so it shouldn't be that big a deal, right?
Yeah. Um, it's been a long time since we've done this chapter, so I think for this one I'm confused at the end. So I calculated the gravitational force because that affects the tension on the string at the bottom, and then also Ft. And I was gonna subtract them, but it doesn't make sense for me to subtract them, even though the vectors are pointing in opposite directions.
Yeah. Let me go ahead and so
I don't know.
let's check in on Ju. So Ju, do you have this velocity now? Sorry, not getting the answer. Okay, so let me talk you through it again here. So um, you said that this step right here makes sense, right? So like the centripetal force is going to be equal to the gravitational force because the tension is 0 at the top if we're looking just for a minimum speed. So does that still make sense? Okay. And then since it is a centripetal force, it's going to be mass times centripetal acceleration, right? And the centripetal acceleration you can always write as v squared over r. So the centripetal force is mv squared over r. Then you just take the things that you know, which are mg and mv squared over r, and you set them equal to each other, and you cancel the mass because there's a mass on both sides, right? So we have this expression g equals v squared over r. Are you still with me on this? Okay. So once we have this expression, we just need to solve it for v. So in order to solve for v, I just multiply r over. So I have r times g equals v squared. So you can write that down at like an intermediate step there. So r times g equals v squared. And then in order to get rid of the square on the velocity, I just take a square root on both sides, right? And that leads me to the expression in pink here. So do you follow all those steps there? Okay. And then so we have V equals square root of R times G. Now the only chance you have of making a mistake here is maybe like your parentheses aren't right or something like that, right? So when you punch it into the calculator, it should look like this. 1.1 times, and sorry, there should be two parentheses here. 9.8. It should look like this. So that way everything is in the square root. Then you can push equals and you should get 3.28. So let me know if you get that. So it really just comes down to, once you get the formula, it's all about just plugging it into the calculator correctly. Okay, cool. All right, so do you need to write anything? Does anybody need to write anything down that's written here? Because I'd like to clear this space and then we'll do part B together here.
I'm good.
Okay, let's go ahead and erase. Okay, so when we're looking at the bottom of the circle, there we go. When we're looking at the bottom of the circle, it's a combination of the tension and the gravitational force that gives us the centripetal force. But now, instead of not knowing the speed, we don't know the tension. So the centripetal force, if we want to write it in vector form, it's the centripetal force is the net force. So maybe we should write one more step here. So the net force is equal to the centripetal force. If the net force wasn't equal to the centripetal force, then this would not be circular motion. So that's something you can always rely on. The net force will always be equal to the centripetal force. Unless you're looking at the case of like a non-uniform circular motion or something like that, which we're not going to actually do on the test. I think I mentioned that all the way back when we covered it. So centripetal force is the net force. You can always write the centripetal force as mv squared over r, but hold off on that a second. Let's sum the forces for Newton's second law. So the net force is equal to the tension, and it's called Ft2 in this diagram. That tension is upward. Let's go ahead and indicate over here when we sum forces the direction we're choosing to be positive. So up is going to be positive in this case. So the Ft2 is pointing up, so it's positive. The mg is pointing down, so let's go ahead and subtract it off. Minus let's put minus. Now I kind of want to get rid of the vector signs. Actually, let's go ahead and get rid of the vector signs. We're only working in one dimension basically, so we don't need these vector signs. Let's go ahead and ditch the vector signs so I can put a minus sign. So Ft2 minus mg. Okay. So this is the net force, the tension minus the gravitational force, and that's got to be equal to the centripetal force. But we don't know what the tension force is. The things that we do know are the gravitational force. Let's go ahead and box some stuff here. So I know this force here and I know this force here. Why do I know the centripetal force? Well, centripetal force, maybe let's put red here. Centripetal force is equal to mass times centripetal acceleration, and centripetal acceleration is v squared over r. The problem is telling me that the ball is moving at twice the speed at the bottom of the circle. So it means I take my answer from the last part, which was 3.28 meters per second. And now I'm saying that the speed at the bottom is, what is that, 6.46, right? So now the speed is 6.56 meters per second. So I know the speed, right? So I know the speed, I know the radius of the motion, that's the 1.1 meters. So I know everything on this side of this equation here. So again, let's recap. We sum the forces, that's tension minus gravity, and that equals the centripetal force. I know what the centripetal force is because I know the radius, I know the mass, and I know the speed. So the only thing I have to do now is solve for the tension force and then plug everything into my calculator the correct way. So the tension force, Ft2, all I have to do is add mg to both sides, right? If I add mg to both sides, then I've isolated the tension force. So the centripetal force plus mg is equal to the tension force. Maybe we can like substitute in some known quantities after this. So the red and blue highlights there are known. So mv squared over r, right? Plus, and then, mg, right? And that's a matter of just plugging it into the calculator correctly. So how do we plug it in? Well, let me go ahead and put the numbers here, and I'll try and write it in a way that is friendly for a calculator. So I'll leave the units out. So 0.15 kilograms for the mass times the velocity squared. So 6.56 quantity squared. Divide that by the radius, which is 1.1. And then I have to do so this is the red piece here. So this is all the red piece. Okay, now plus mg. So m again is 0.15 and g is 9.8. And so this is everything. This is the blue piece here. You can just punch all that in the calculator all at the same time there. It should give you a nice answer. So while you guys are calculating that, so please calculate that yourself with your calculator right now, just to get some calculator practice. I'm going to go ahead and do that over here. Okay, that's that part. And then now this part. Okay, and it looks good. I end up with 7.34 newtons.
I got the same.
Awesome. Okay.
So just to kind of recap to make sure I'm understanding it correctly, because I think the vectors and the quantities confuse me when I put it into equation. So because we assign the upward direction for Ft a positive, the mg, the gravitational force, is a negative vector, like directional quantity, or gosh, I hope you know what I mean, but
Yeah,
it's
yeah, it makes
negative
sense.
because of the axis.
Yeah.
Um, so because the vectors, oh, actually that doesn't make sense to me anymore. We, why did you decide to do F net equals FT minus mg instead of plus mg?
Okay, so these two vectors are in opposite directions, right? So you have tension
Yeah.
up and you have
Uh-huh.
gravity down.
Mm-hmm.
So no matter what direction I choose to be the positive direction, these two will have a relative minus sign
Right.
because they're working against each other.
Uh-huh.
That's pretty much it.
Oh,
So
that's why you put the minus in there?
yeah, I wanted to put the minus in there on purpose because they're
Mm-hmm.
working against each other. If I left the vector signs, then I would have had an expression like this, which is not technically incorrect because G is a vector which is minus
Mm-hmm.
9.8,
Okay.
like Y hat or J hat. So
Yeah.
it's a vector that has a negative direction. So
Okay.
technically this would be correct, but I think having the vector signs in there can add like an extra layer of complexity.
Mm-hmm.
We know they're working against each other, so let's just put a minus sign here
Okay,
and
gotcha.
just be done with it.
Yeah. Okay, that makes more sense then. Okay,
Okay.
thank you.
Yeah. Ju, were you able to reproduce that answer and then let me know if you have any questions about it? Okay. Do you have any questions about anything there? Okay. So let's go ahead and move past this second example now. And I'd first like to highlight something here. So um, here are some extra problems I would recommend if you have the extra time to do them before the test, is to take a look at examples 5.6 and 5.7 in the book. So this is good for chapter 5 review. We're not going to do them here. We're going to do other problems, but these are like two extra ones that would be good to take a look at. And since they're examples in the book, they have a nice, well uh, documented solution there in the textbook. So it gives you all the reasoning and the right formulas and everything to get the answers. So take a look at those if you guys have time. Remember, there's also a test to practice assignment that was posted on Mastering Physics as well. So there's plenty of practice out there for you guys. But make sure you work on stuff that you feel like you're weaker in. Don't work on stuff that you've already kind of got a good understanding of. Okay, so let's go ahead and go to this next example here. Now, this chapter also covers the gravitational force, so Newton's law of gravity. So that's what this next example is. So a 50 kilogram person and a 70 kilogram person are sitting about half a meter apart on a park bench. Part A, what is the gravitational force of attraction between the two people? And then part B, explain why that force isn't felt by either person. Okay. So I'll go ahead and let you to work on that. And then if there's a question or something, just let me know. And then maybe you guys could each write in the chat. You could write just from memory. Don't look it up. Try to write it from memory. The equation for the force of gravity between two masses. Can you remember that?
It's the gravitation. You want me to write it in the chat or say it
Yeah,
out
write it in the chat so that way you're not saying it out loud. So that way, other people can think about that as well.
I also wanted to ask, do you want us to have like the gravitational constant memorized, or is
No,
that
I'm
something?
giving that to you. No, I
Oh,
give
okay.
all the constants. Yeah.
Okay. But all of the formulas should be, all the relationships and definitions should be memorized.
Yeah, and if there are certain formulas which I think are kind of a little bit difficult to have memorized, then I usually give them in the question.
Okay, awesome.
Like for
Thank
example, moment of inertia of a sphere, moment of inertia of a
you.
disk. Those ones will be given in the
Okay.
actual problem statement inside the question itself. So they won't be on the front page. They'll just be
Mhm.
right there in the question.
Thank goodness. Okay. Those ones are harder to remember.
Yeah, for sure. I think probably what people should be doing, and I think I did mention at the beginning of the semester, but I didn't really like keep emphasizing it, is you probably should just always be making flashcards every time we come across a new formula, and just spend a little bit of time, um, like when you review your notes, to go over those flashcards. I think it helps a lot for memorizing the formulas, because we just use the same formulas over and over and over again. Every time we get to a new chapter, we're using like older formulas over again. So it's super important to have them memorized.
Yeah. I actually found it really hard for some reason because I think it's been like 3, 4 weeks since we touched chapter 5 to review it, even though the material isn't like super crazy complicated. I was wondering if for the next exam, maybe we could do like, if you'd be open to like a study session for like an hour after the first 2 chapters. So we have like a mid, like,
Possibly, yeah, that's a possibility. I will say that, yeah, chapter 5 and 6 were a long time ago. But if
mhm,
you look at the number of problems we're going to have in this review session on chapters 5 and 6, like it's
mhm,
going to be a lot. So,
that's true.
like I said, so
Okay.
all of these problems here that I have here are all from 5 and 6.
Okay.
So hopefully after we get through these, then you'll be feeling pretty good about that older
Okay.
stuff. On top of that, like the stuff in 7, that's momentum. Um, doesn't really have anything to do with these like last 2 chapters, but then chapter 8 has a lot to do with chapter stuff from chapter 5, like the circular motion type stuff.
Mhm,
So hopefully by going over a lot of chapter 5 here, it's also helping a little bit with chapter 8. But
mhm.
we'll see. We'll see how it goes. And any extra
Okay.
time we have, we can always go over extra examples.
Okay. Thank you so much.
Ju, you never put in the formula for the force due to gravity. Um, Christine has put it there. Are you able to reproduce it? Okay, that's one that you should have memorized. It's a super important equation. It's one of the ones you should have memorized for the rest of your life after you finish this class. Newton's law of gravity. So there's a gravitational force of attraction between any two objects in the universe. It's the product of the masses divided by the distance squared. And then this big G is just to fix the units up. You just want to fix up the units, so you put this constant in front. So I'll go ahead and write it now. So big G, product of the two masses, m1 and m2, divided by the distance between them squared. Yeah, there's a couple formulas like this that you should just have, you should just fully understand for the rest of your lives after you get through this class. Newton's law of gravity is one of them. Obviously, Newton's laws. Um, uh, I mean, yeah, there's just so much stuff that you should just have memorized by the end of this class, and you should just never forget it. Okay, Christine, you have a numerical answer, then you can start thinking about part B.
I actually don't. I don't know.
You can think about the magnitude of that force compared to the force of gravity, the person's weight.
Okay, that's what I was thinking. But then, considering that do we really feel our? I'll think about it.
You don't necessarily feel the gravitational force, but there's another force that's related to that, like if you're sitting on a park bench. All right, Jude, do you have an answer here for this question? I just realized I probably should have given you guys this constant here. So big G is 6.67 times 10 to the negative 11 Newton, what is it? Newton meter squared per kilogram squared.
We don't feel gravity because of the normal force, right?
You feel the normal force. You don't feel the actual force of gravity. That's why
Oh, yeah.
astronauts, like on the International Space Station, would feel weightless
Mm-hmm.
because they're
That's
they're
right.
they're falling under the influence of gravity, right?
Mm-hmm.
There's no there's no normal force acting on them, like because they're walking on something, right? Because they're not actually walking on anything; they're kind of floating as
Mm-hmm.
they're in free fall. Okay, Ju, what's the status here? I think I'm going to start plugging in some numbers here. 6.67 times 10 to the negative 11. This is one where you really want to be careful on the calculator. So there's big G. Multiply by the masses of the two people. So there's a 50 and there's a 70 kilogram person. And now here's where mistakes can be made, is when you're dividing. So whenever we divide, we always want to make sure we put this number in parentheses here. So 0.5 on the bottom, and then don't forget to square it and make sure you put it in parentheses like this. And then what we end up with here, I'll go ahead and calculate along on the side. 6.67 times 10 to the negative 11 times 50 times 70 divided by 0.5, and we square that 0.5, and I end up with an answer 9 point, well, technically if we want to be accurate to the appropriate number of significant figures here, the radius is only given to one significant figure, so we'll leave it at 9 times 10 to the minus 7 units of newtons.
You're
So
missing.
I think Christine, you got that one right. Jude, were you able to get that? And Christine, did you have a question?
No, I was just commenting how bad I am at sig figs today.
Oh, I mean, it's just a little bit of practice with it here and there. Like usually I forget them, and then it comes back to me as soon as I like review it. It's not that big of a deal though. We're just doing problems to practice the physics, right? We don't really care. We're not in the lab. We don't really care too much about the sig figs here, right? So, okay, good. So now let's talk about part B here. So explain why that force isn't felt by either person. So if we had to write an answer here for this, this is what I would write. The force is not felt by the people because this force is very small compared to other forces acting on those people. For example, the gravitational, or excuse me, the normal force due to people's weight, which acts to prevent them from falling through the bench. And then another explanation, well, I just say this in words actually. This is really probably the best argument here. Another explanation might be something along the lines of, suppose there is a gravitational force of attraction between those two people that is going to be felt. But there's also a friction force between the people's, their butts and the bench, right? And so there's no net force on those people, even if they are gravitationally attracted to each other. There's a friction force that's going to counteract that. And so there's not going to be any acceleration due to that force, and therefore they won't experience that force. Furthermore, if you want to get like really technical here, you could imagine two people in outer space and they're really far away from anything else. Then they would have that same gravitational force of attraction, and then they would start accelerating towards each other, right? And that acceleration would be very small. And they still wouldn't feel that force because there's no actual contact with anything, right? They're just out in outer space. There's no actual contact between them and anything. And so there's no neurons firing, so to speak, in their body telling them that they're feeling something, right? So there you go. There's your answer for part B there. Are there any questions about that? Okay, so no questions. Let's go ahead and go to the next example then. I think I have to click out. There we go. So the next question is a conceptual question. Just kind of test your knowledge of Kepler's laws here. So which of the following best describes Kepler's third law? The period of orbit is proportional to the radius of orbit. Planets go around the sun. The centripetal acceleration is proportional to the speed squared. Or the final choice, the square of the period is proportional to the radius cubed for any orbit. So just pick a letter for your answer. Yeah. So pick a letter A, B, C, or D. Only one choice is correct here for this question. Answer B is not so funny if you think about the time period between the mid 1400s to early 1500s when Copernicus was fighting against the church, trying to say that the sun was at the center of the solar system.
That's also true, but also very long ago.
Yeah. Ju, do you have a choice here? Do you know which? Do you have an idea of which answer it might be? Okay. We can give you some time.
How's adjusting to your move to SoCal?
Um, it's fine. My schedule is pretty messed up right now, though. I'm getting up pretty late and going to bed like super early in the morning.
You don't have any morning classes?
No, I have like 1:30 to 4:40, and then 6:10 to 9:20, and then your guys' class is the 5:40 to 8:50, so they're all like kind of like night classes.
I guess that makes sense. I mean, if your sleep schedule works for your work schedule, I think it's fine.
Yeah, it's a little bit tough to get up for the 1:30 class though.
Oh.
Yeah, working on it though. All right, Jude, do you have an answer here for this? Let's go ahead and go over it now. Okay, yeah, I see you chose D. D is the correct answer. Let's go ahead and take a look at these here. So the period of the orbit is proportional to the radius of the orbit. That's saying T is proportional to R. That's not true. Planets go around the sun. Yeah, but it was Copernicus who came up with this. Copernicus, I think that's how you spell his name. The centripetal acceleration is proportional to the speed squared. So AC equals, or rather is proportional to V squared. It was probably Isaac Newton who came up with this equation, the centripetal acceleration equals V squared over R. The square, if it wasn't Newton, it was probably Galileo. The square of the period is proportional to the radius cubed. I guess it technically could be Kepler, so maybe I should look up the history on this equation myself because I don't know it. Anyways, the square of the period is proportional to the radius cubed for any planet. Yes, this is exactly what Kepler came up with, and he used this equation to relate the orbits of the different planets. Matter of fact, I can tell you exactly what Kepler did. So there was Mercury, Venus, Earth, Mars, blah, 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 all the way out to Saturn. Those were the known planets at the time. And Kepler, using observational data with his partner was actually like a wealthy man. His name was Tycho Brahe. He was like a wealthy nobleman who had an observatory and a lot of money. And so he partnered up with Galileo, who was more of like a commoner, like amount of wealth. And together, using the nobleman's data, Kepler was able to write down his law. So basically, what he did was he wrote down the radius and the periods of all of these 6 planets, and then he worked out basically the relationship. And the way you actually go about doing this is you calculate ratios like r divided by t, and then maybe you'll do r squared divided by t, and maybe you'll do something like r divided by t squared, and you're going through different powers. You might try like 3/2 for r and t squared, and you can just go through those values or those guesses until you come across something where it looks like magic. All of a sudden, when you choose r cubed and you choose t squared and you take the ratio, you end up with the same value or approximately the same value for all of those planets. And then boom, that's a clue. You've found yourself a natural law, so to speak. And it was Isaac Newton, after he came up with his 3 laws and the universal law of gravitation, that showed the actual relationship between t squared and r cubed. So let me see if I can remember. It's something like t squared is 4 pi squared over g r cubed. Does that have the correct units there? Let me go ahead and double check. So Kepler's 3rd law. Yes, so that is the correct equation there. Oh no, excuse me. I'm missing a mass here. And this is the mass of the object at the center. So for example, if you're looking at the planets going around the sun, then the big M there is the mass of the sun. If you're looking at something like the moon going around the earth, then the big M is the mass of the earth. Or if you're looking at like the International Space Station going around the earth, then the big M again would be the mass of the earth. If you put a satellite in orbit around the moon, then the big M would be the mass of the moon, right? So that's how you interpret that equation. There won't be a question on the exam that requires you to have this question memorized. If I ask you to use, this formula, if I ask you to use this formula on the exam, I'll give you that formula. Okay. So let's go ahead and go on to the next question then. And thus begins the chapter 6 review. So chapter 6 is all about work and energy. And since we're coming across now the first question here on the chapter 6 review, I will walk us through this one to kind of warm us up to the concepts that we see in this chapter. So let me know if I need to explain something a little bit more or slow down a little bit. So we have a diagram over here on the right. It looks like we have a hiker with a backpack. He's climbing up this this little hill here, a distance h, a height h, a distance d along the hypotenuse. Part A says to determine the work a hiker must do on a 15 kilogram backpack to carry it up a hill of height 10 meters. Assume the hiker moves with constant velocity. Okay. Assume the hiker moves with constant velocity. Why don't you guys, I can get you guys involved a little bit here on this one. Why don't you guys think about maybe what kind of formula I might need to use here to do part A, and then I'll go ahead and go through solving the problem. But you guys maybe write in the chat if you have an idea of what formula I need to use. You guys have any thoughts? What's a formula for the work?
It's force times distance, but oh, okay, yeah, it's force times distance, but we can transform force into mass and acceleration, and then find the distance by using the triangle, right?
Right. So the force that we have to overcome is the force of gravity, right? And since we're being asked how much work the hiker does to carry the backpack up the hill, then it's going to be equal to the mass of the backpack times the gravitational acceleration. So that's going to be the gravitational force. The direction of the force has to be vertical over that distance h. The force could be at an angle like this up the hill if the hiker started from like a walking speed and then started to accelerate up the hill and began running up the hill. Then the force would maybe be at an angle like this, but it says moves with constant velocity, so the net force is 0, and we're just looking at balancing out the weight of the backpack. So the force that the hiker must exert on the backpack to move it up that hill is the weight of the backpack. Okay. Now that's just the force part. What about the distance part? Well, the distance is the height, right? We have to move that backpack parallel to the force. So that's something I didn't quite write there yet, is that the force has to be parallel to the distance traveled, or the displacement rather. Okay, so let's go ahead and maybe we'll change the color here. So the amount of work, this is part A, is going to be mg times h. And again, that's because we're moving with constant velocity. If we accelerated up that hill, the answer would be different. So m is 15 kilograms. Now let's go ahead and leave the units off so it's calculator friendly here. So 15 times 9.8 meters per second squared, and then times the height of 10 meters. And what do we come up with? You guys can go ahead and calculate along with me. So 15 times 9.8 times 10, and we end up with 1,470 joules. That is the unit of work and energy, joules, right? So joules, you can think of as it is kilograms times meters squared per second squared, or you can think of it as newtons times a meter, which happens to be the same units as torque. But torque and energy are two different concepts, so you don't really want to mix those two ideas up. You want to use joules for energy, and you want to use newtons times meter for torque. Okay, so I'm going to go ahead and remove that now. And now we can go ahead and tackle part B. How much work does gravity do on the backpack? Well, the amount of work that gravity does on the backpack is going to be the gravitational force on the backpack times the displacement, but we need to keep in mind the vector nature of the force of gravity. So the force that we exert is an upward force as we lift the backpack up, right? So the force is up and the displacement is also up. Well, the gravitational force is down, but the displacement is up. And so the gravitational force is not parallel to the displacement. It's what we'd call anti-parallel. So it's in the opposite direction. So minus the force of gravity times the height h, which gives us minus the mass times gravitational acceleration times the height. And we already plugged in these numbers. The only thing that's different is the minus sign. And so we get minus 1,470 joules for the work done by the gravitational force. Now you might be scratching your head a little bit, and that's understandable. Why is the work done by the person the same as the work done by the gravitational force? The answer lies in the fact that we have moved with constant velocity. Okay? Had we accelerated, then it would be a completely different story. Then the force that we would exert would be different than the force of gravity. If we were going to accelerate up that hill, we would have to exert a bigger force than gravity, right? And so the amount of work that we would end up doing would be more than the amount of work that the gravitational force does. And then, of course, we would end up with more kinetic energy at the top due to the fact that we accelerated, right? We'd have a larger speed. Okay, part C says to calculate the net work. And the net work is simply the work that we did plus the work that the gravitational force does. So you take all of the individual works that were done by individual forces and you sum all of them up. That's the net work. And so we end up with a big fat 0 for the network. Again, the reason the network is 0 is simply because we're moving with constant velocity up that hill. And so rest assured that if you move up a hill with constant velocity, there's going to be no net work done in that case. Any questions about that example there? Okay, so we'll go ahead and get you guys started on the next one. And here it is. A car traveling at 60 kilometers per hour can brake to a stop in a distance of 20 meters. 1 kilometer per hour is equal to 1,000 meters per 3,600 seconds. Okay, and so that number comes out to, let me go ahead and just calculate it. So it comes out to 0.27, and this is a repeating 7 here, meters per second. So you could round it to 0.28 meters per second. Okay. So go ahead and get started on that one. Whenever you have a question like this, it's giving you a speed, it's telling you that the car is braking. That means there's a force on the car, right? And that force is stopping the car in a distance of 20 meters. So you should be thinking about work done by friction. So you have a friction force due to braking. So there's an amount of work that's done there over that 20 meters of distance or displacement. And the car is losing velocity, or it's losing speed as the car brakes. And so that's means it's losing kinetic energy. So maybe there's an expression which relates work and something to do with kinetic energy. Maybe you guys can tell me what that is, and then I'll write that formula down. So you can say that in the chat if you want.
Wait, what was the question?
Is there a relationship between the amount of work that's done and kinetic energy?
Isn't it the same?
Not exactly. There's one detail there. There's one detail there that you're missing. It's not work equals kinetic energy. It's work equals something kinetic energy. Can you think about what that is?
Oh, the change in kinetic energy.
Exactly. Exactly. You have to put change in kinetic energy. So when the car brakes, right, there's going to be a bunch of work done on the car to make it come to a stop. And that amount of work is equal to the change in kinetic energy. And you're going to need that relationship in order to solve part A. Okay, so I'll read part A now. Part A, if the car is going 120 kilometers per hour, what is the stopping distance? So the speed is now twice as big. What's going to happen to the stopping distance?
It's gonna be larger.
It's going to be larger, right? But
Mhm.
by what factor, right? So that's what we want to calculate now. We want to see, is it going to be like 40 meters now? Is it going to be more than 40? Maybe it's going to be only a little bit bigger than 20, right? That's what we want to calculate. So we've been going for about an hour and like 20 minutes or so, right? So maybe it would be a good time to just kind of like work a break in with this problem here. You guys want to do that?
Yeah, we can. I'm fluid.
Okay. All right. So Ju's also good with that. Okay. So maybe we'll meet back in like 10 minutes then. Meet back at 9:36 and we'll continue. Any questions you guys have, you can write them in the chat and I'll respond to you if I catch it. Um, so I'll see you guys soon. Okay, I'm back. Let's go ahead and take a look now. First thing to do is to write down the work energy theorem, the work done by the car, or excuse me, the work done on the car by the friction force due to braking is going to be equal to its change in kinetic energy. Well, kinetic energy initially is 1/2 mv squared. The initial squared, let's say. What's the kinetic energy final when this car comes to a stop? Well, if it comes to a stop, its velocity is 0. And so then the kinetic energy must be 0. How about the work done by the friction force due to braking? Well, the force on the car must be opposite to the direction of motion because the car is coming to a stop. So we'll put minus F times D. This work must be equal to the change in kinetic energy by the work energy theorem. Okay, so minus F D is equal to, and then our final is 0, and then we subtract our initial, so minus 1/2 mv initial squared. And so we end up with FD equals 1/2 mv initial squared. We cancel the minus signs on both sides. But now we need to do something about this force here. What's this force? Well, a force can always be written as m times a. The net force on the car is this friction force, so we'll write that down as mass times acceleration times the displacement. In other words, work is mad. It's 1/2 mv initial squared. And now we see that the masses cancel here. And then what we can do is we can say that the stopping distance d is going to be equal to v initial squared divided by, excuse me, twice the acceleration. So just dividing the acceleration over there. Well, if that's the case, if I know the car stops in 20 meters with a velocity of 60 kilometers per hour, if I were to double that velocity, then I would have to square the velocity. And so increasing the velocity by a factor of 2 increases the stopping distance by a factor of 4. So d is proportional to v squared. So that's going to give me 4 if I plug in 2v, right? So this is twice v. And so this is going to end up being 4 times the distance. Okay. Is everybody with me on that? Are there any questions about that? Okay. So stopping distance is proportional to v squared. So doubling the velocity gives us 4 times the stopping distance. Now the question is, oh, and actually I did not give you a mass to do part B. Yeah, you definitely need the mass for part B. Was that your question earlier, Christine?
Yeah, that was my question.
Oh, okay. Oh, I didn't notice you said second part. Okay. That was my mistake there. Yeah, you do need the mass for the second part. Let's go ahead and say we have the mass of a typical car here, 1,500 kilograms to do part B. So the kinetic energy can be calculated right here. Initial kinetic energy. So for part B, we have 1/2 1,500 kilograms times the initial velocity squared, but we better make sure that we put that velocity, excuse me, in meters per second. Well, 1 kilometer per hour is 0.28 meters per second. So let's take the velocity, 120 kilometers per hour, and multiply it by 0.28 meters per second per 1 kilometer per hour. Just to convert that kilometers per hour into meters per second. On the test, I won't make you convert units like this. So this is more of just like part of the practice problem here, right? So you notice that earlier we calculated how many meters per second 1 kilometer per hour was. So you can notice here that these units of kilometers per hour will cancel with those units there, and we'll be left with meters per second. So all we have to do is make sure that we square 120 times 0.28. That's our velocity in meters per second. Okay, so I'll go ahead and calculate that. You guys can follow along. And we get 25, and I'll just cut it off here, 25 kilojoules of kinetic energy. So 25,200 joules is what I got for that answer there. Cut it down to 2 sig figs, 25,000 joules, or 25 kilojoules, or 25 times 10 to the third joules. Any answer like that would be acceptable. Any questions about that one?
I got a different number. I got.
Oh, you know what? I forgot to square.
Oh, okay.
I forgot to square. I see it there. Oops. So the number is actually much bigger, huh? 846,000.
Yeah, that's what I got.
Rounding that to 85. So 850 kilojoules. There we go. I was just talking about how you got to make sure we square it. Okay, so no questions on that one then. We'll go ahead and go to the next one. Okay, and so here we go. Use energy conservation to determine how fast a rock impacts the floor if it is dropped from a height of 5 meters. So we're looking at a height of 5 meters. How fast means what's the velocity, right? So we're looking to calculate a V. And we're looking to use energy conservation here, right? Which means energy initial equals energy final. Okay, so do you guys need me to help kind of get you started on it, or you kind of have an idea of what to do?
Can you start us on this one?
Okay, so the starting place here is E initial equals E final. And then you want to recognize, based on the wording of the question, what kind of energies are at play here. So if we're dropping a rock from a height of 5 meters, that means you're holding it up, right? And just letting it go. So no initial velocity, which means no initial kinetic energy. So it's all potential energy initially. So potential energy initial is equal to, and then what's the final energy in the problem? Well, if the rock falls the 5 meters and hits the ground, well, at that instant, it would have no potential energy, right? Because it's 0 meters above the ground. However, it is going to pick up some velocity, and so it's going to have no potential, but it's going to have a bunch of kinetic energy. So kinetic energy final here on the right side. So that's a good point to start there. Does that help get you going? Okay. You definitely want to have gravitational potential energy of mgh or mgy and kinetic energy 1/2 mv squared. You got to have these ones memorized. Those are crucial equations. Those are like some of the equations you want to have memorized for the rest of your life after you're done with this class. And getting the velocity that this rock hits the floor at is just kind of like the first part of this question. And the second part of this question is all this text right here. Don't worry about this just yet. This is actually just one question here. It's kind of like a little multiple choice question that we'll do after. Okay, you calculated 10 meters per second. Okay, let's see what Ju comes up with. Yeah, no rush. I'll go ahead and write some more stuff over here on the side. So potential energy initial, mgh, is equal to kinetic energy final, so 1/2 mv squared. Okay, I'm going to go ahead and write a little bit more now. The first thing that I notice is that the masses on each side of this equation cancel out. That was something that Galileo figured out, right, before Newton, that the mass shouldn't determine anything about the motion of the object. And so we can solve for V here. So we start with GH equals V squared over 2. Divide by 2. Oh, good job. Okay. So GH equals V squared over 2. You can multiply the 2 over, right? And then we can square root both sides, and that tells us that V is going to be equal to the square root of 2GH. That's a formula we've seen many times now, right? So once we got that, then we plug everything in, and we just make sure that we got our parentheses so that everything is in the square root, right? Okay, I'm just going to go ahead and trust the both of you on this answer here. I think that sounds good to me. 5 meters per second is going to take 1 second to fall, I think. And so your answer probably was 9.8 meters per second. You round that to 10, right? Okay, let's take a look at the next part now. If a non-conservative air resistance force acts on the rock as it falls, which of the following are true? So we have a non-conservative force. What do non-conservative forces do? Maybe you can give me a little like one sentence answer like in the chat. So what does it mean for a force to be non-conservative? Energy is lost. Okay, I like that answer. So if energy is lost, then we can take a look at maybe this first, let's do another color here. This first statement here, statement A. The speed of impact will be lower due to energy lost to the non-conservative force. So this is kind of exactly like what you were saying, Christine. That energy is lost. So would you conclude that this statement is true?
Yeah, I think so.
Okay, so we're going to say this one is true. I'll go ahead and put a question mark there. All right, statement B. The rock no longer has potential energy because of, oh, and I misworded that a little bit. It should say because of the, so of the non-conservative force acting on it. So the statement is the rock no longer has potential energy because of the non-conservative force acting on it. Okay, Christine says false. How about you, Ju? What do you think about this statement B here? The rock no longer has potential energy because of the non-conservative force acting on it. Sounds false. Okay, so we'll go ahead and put false here. Again, I'll put a question mark here. We'll look at all of them at the end. Okay, last, statement C. The kinetic energy of the rock just before it impacts the ground will be less by an amount equal to the total amount of non-conservative work done on the rock. That one's kind of a mouthful there. I'll read that one more time. The kinetic energy of the rock just before it impacts the ground will be less by an amount equal to the total amount of non-conservative work done on the rock. So what do you two think about that one?
I have to read it again. Hold on. I think we both said true for part C.
Okay. Yeah. I was actually looking at the grade distribution for the last test. Okay, so we think true on this one. All right, let's go ahead and evaluate each of these statements now. So A, the speed of impact will be lower due to energy lost to the non-conservative force. This is true. Okay, so this is true because there will be energy taken away by the air resistance force. So the net energy, the total energy at the top, when it's all potential energy, will be diminished by that non-conservative force. So less energy overall will eventually become kinetic energy. Okay, B, the rock no longer has potential energy because of the non-conservative force acting on it. This is not true. It still has gravitational potential energy. The gravitational force is a conservative force. And so we can still have potential energy due to the gravitational force. You cannot define potential energy for a non-conservative force. But since gravitational force is conservative, then we do have potential energy. So this one is false. So that's good. Check, we got that one right. The kinetic energy of the rock just before it impacts the ground will be less by an amount equal to the total amount of non-conservative work, done on the rock. That is true. So that one is also true. The way to go about calculating this in your expressions is to say that the initial energy minus all of the work done by non-conservative forces is equal to the final energy. That's how you do it. It's that simple. You just subtract off the amount of work done by the non-conservative force. So your initial energy could have potential, it could have kinetic, right? Your final energy could have potential and kinetic as well. And all you would do is subtract off the non-conservative work from the initial energy because you know the final energy is going to be less. Sometimes you'll see this term written on the other side as a plus work non-conservative. That's equivalent, right? It's just another way of looking at it. I tend to like putting it on the left side because then it explicitly subtracts from the initial energy. Okay, so we'll go ahead and go to the next one. And this is the final one that we have on the left side, but I have some more on the right side over here, up at the top. So this is a conceptual question. If a variable force is applied to an object, the work is calculated as what? So the average force times the displacement, the slope of the force times the displacement, the area under the graph of the force versus displacement for a given displacement. Which of these is the correct choice here? So A, B, or C. If a variable force is applied to an object, the work is calculated as blank. Okay, we have one answer. Maybe you're unsure about that answer, so just think about it a little bit more. Not sure? Okay. So what you want to remember, and I'm going to just start by giving a hint, so maybe you guys can figure out the answer, like just with a little bit of a hint here. You have to remember that work is equal to force times displacement, but you have to remember it in this way here. It's really important that you remember the delta x equation instead of like F times D. Because whenever you see deltas like this, you have to think in terms of calculating areas, right? So I'll just give you another example here. So acceleration is delta v over delta t, right? And so if I rewrite this as acceleration is delta t equal to delta v, then you know that this here, remember when you're going from acceleration to velocity, that's area. It's because of this delta right here that we're multiplying by, so delta t. So this is area under v versus t. Okay, so here we have F times delta x. That's going to be area of F versus x. Okay. Oh, excuse me. I miswrote that there. There's a mistake there. Not area under V versus T, area under A versus T. Right? So now it looks the same as what I wrote with the equation above. So area under A versus T. So here's A and T. Here's A and T. It's area under A versus T. So here's F and X. So it's area under F versus X. Okay, so it's not A, it's not B, it's answer C. Okay, so it's the area under the graph of F versus X for a given displacement. Let me go ahead and off the cuff here, go over an explanation I gave for the energy stored in a spring. Remember, we kind of took a look at an example where we have a spring with a mass attached to the spring, like so. And when the spring is stretched, if the spring is stretched, suppose the spring's equilibrium position is here. What does equilibrium mean? Equilibrium means no net forces, right? No net forces. So this is the equilibrium position of the spring. And as we know, if we've ever played with like a slinky or something like that, right, or a spring, when we stretch it out, it wants to come back to its equilibrium position. So the equilibrium position is there. That means we must have stretched this thing by an amount delta x. This is the stretching. Let's maybe change colors here. Go ahead and change colors. So this is the stretch of the spring. And the spring could also be compressed. If we were to compress the spring, then delta x would be on the left side of the equilibrium point that we've drawn here. So you'd squish the spring together, right? So if delta x is the stretch, then the force, which I'll draw in red, is a restoring force. And it's given by what we call Hooke's law, the magnitude. Let's go ahead and write it with vectors first. The vector force here is minus k, which we call the spring constant. It's different for every spring. It's different for every spring, times the displacement, delta x. But delta x has a vector there. Delta x is to the right in this case, while f is to the left. That's why we have this minus sign right here. So opposite direction. I didn't finish writing this. This is called the spring constant. And it's different for every spring. Go ahead.
Quick clarification. So if it was a compression instead of a stretch, which I don't think we actually went over in class, if it was a compression, then it would be a positive spring constant times displacement.
No.
Oh.
If it was compressed, then delta x would be to the left, and the restoring force would be to the right. So there's always a minus sign.
Oh, because literally they're, oh, I see. Okay, thank you.
And so if I want to write this down as magnitude, I can just get rid of, if I want the magnitude of f here, right, then I can just write it as f equals kx. And I just understand that the direction I can figure out by looking at a picture, right? So there's also that way of looking at it too. Like you don't care about the direction in your equation, you'll figure out the direction later, right? So when it's compressed, then that means the force wants to uncompress it, or it's called decompress, right? And then when the spring is stretched, then it's under tension, and the restoring force wants to bring it back to equilibrium. So the restoring force actually wants to compress the spring again. So if you stretch it out, the restoring force wants to compress it again. If you compress the spring, then the restoring force wants to decompress the spring. So always in the opposite direction. And what ultimately ended up happening was we noticed that the force here depends on x. And so this is an example of a variable force. The plot of the force as a function of the displacement looks like this. It's a straight line, and it has a slope which is equal to the spring constant for that spring. And so in order to calculate the work, we would have to calculate the area of this triangle here. Let me use another color here. So the work equals the area. So you guys tell me, how do I calculate the area of this triangle here? How do we calculate the area of the triangle?
1/2 force times displacement.
Right, so start with 1/2 base times height, and then you can see that the height here of the triangle is f, and the width of the triangle is delta x. So work equals 1/2 F times delta x, and F is K times delta x. So 1/2 K times delta x squared. So that's another example of a potential energy being defined by a conservative force. So in this case, the restoring force here is a conservative force, and so we can assign a potential energy of 1/2 kx squared for that stretched spring or compressed spring. And whether you compress the spring or stretch the spring, as long as delta x is the same, you've stored the same amount of energy in that spring.
Is the restoring force ever non-conservative?
No, only forces like friction are going to be non-conservative.
Okay, all right, thank you.
So like, for example, if you go to the next semester, we'll talk about like the electrical force or the magnetic force. And in both cases, or actually, excuse me, only the electric force is conservative. Once you have like magnetic forces involved, then it changes slightly. Okay, so let's go ahead. If there are no questions on this one, we'll go ahead and go to the next one. Okay, so let's go ahead and go to the next one. Go all the way up here, then scroll over, and I have one here. Okay. So a 60-kilogram jogger runs up a long flight of stairs in 4 seconds. The vertical height of the stairs is 4.5 meters. Calculate the power output of the jogger. How much energy was required to climb the stairs? Okay. So power and energy. How do we figure those things out? Do we have any ideas here? How do we define power?
Power is the mass of the object times its velocity.
Mm-mm. No, power is energy output per unit time. You're thinking of momentum, which we use like a lowercase p. Power is capital P, and capital P is an amount of work over time. We could put like delta T here if we want. Work, or maybe we could write it as a change in energy per unit time, something like this. And then how are we going to go about calculating that power though? Because we're looking at an example here where we have a jogger. We've been given the mass of the jogger. We've been given the time it takes. We've been given the height of the stairs, right? So we weren't given the energy. So how are we going to go about getting the energy in order to calculate the power? So what is the change in energy for this jogger? If the two of you want, it's almost been 3 hours. Like we have about 40 minutes left, right? So if you want, we can try and go over some of these examples like a little bit quicker, and I kind of just go through them, and you guys, I'll maybe ask a question or two here or there. So we can go quicker, we can go over more examples, or do you guys like the pace that it's at now where you get to work on them? What do you guys want to do?
Um, I think it's really helpful the way that we're doing it.
Okay.
But I also want to get through more problems. So maybe yeah, we can speed run it and then I can just review it again and retest myself on these questions.
Okay. And Ju, you're okay with that too? Okay, so I'll go ahead and pick things up from here because one thing that's going to happen here is we're going to run out of questions, and then I'm going to have to bring in new questions and we'll go over those as well. So, how do I get the energy? Well, this is a jogger that's running up some stairs. So, when somebody runs up the stairs, they gain potential energy. So, the change in energy here is nothing but the change in potential energy. And the change in potential energy is mgh. So mgh over delta T, we can plug all of that in. So the power is 60 kilograms times 9.8 meters per second squared times the height of 4.5 meters divided by the 4 seconds that was given in the problem there. Go ahead and punch this in on the calculator. You guys calculate along with me to make sure that you get some practice with your calculators. And I end up with 661.5. Let's go ahead and round it to 660. That has units of watts or joules per second. Energy per unit time. Okay, how much energy was required to climb the stairs? Well, we can just take our knowledge from before that the potential energy changed by an amount mgh and just calculate how much energy was required. So we do mgh, or we could just take the answer we just got and multiply by 4 seconds, right? So either case works there. So I'll just go ahead and do this. So it's 60 times 9.8 times 4.5. And you already have this thing saved in your calculator, so you could just like clear the division by 4. And then what you get on your calculator should be 2000, let's just go ahead and round it. So 2.6 kilojoules. So round it to 2 sig figs there. So 2,646 joules, round that to 2 sig figs, 2.6 kilojoules. Do we have any questions about that? Okay, Christine, are you good?
Yeah, I think so.
Okay. All right, so we'll go ahead and go to the next one then. Try and keep a little bit quicker pace. Now we're into chapter 7. So I should probably have put that there, chapter 7, which is all about momentum. So here we have an example where we're dealing with some train cars. So part A, calculate the momentum of a train car, which has a mass of 7,600 kilograms and a speed of 13 meters per second. So momentum, we use the letter lowercase p, and it's a vector. Whereas power, we use capital P. It's not a vector. It's an amount of energy per unit time. So that's not a vector. Energy is never a vector. P, momentum, is based on velocity, so it is a vector. So it's mass times velocity. And since velocity is a vector, momentum is also going to be a vector. So mass times velocity for this train car, well, we're not given any directions or anything, so we're calculating the magnitude of the momentum. So we'll use P equals mass, 7,600 kilograms, times the speed instead of velocity, So 13 meters per second there. So 13 times 76, 13 times 7,600 there comes out to 98.8 thousand. So I'll put times 10 to the third. And momentum always has units of kilograms meter per second. You could also technically write those units as newtons times a second. That technically works as well, though you don't see that very often unless you're dealing with impulse, which is a change in momentum. Any questions about that first part there? That's just application of the definition of momentum. And Ju, you're okay too? Okay. All right, so question B. Now, each of these parts is kind of like their own somewhat, like kind of a question on their own. So question B, if the train car collided elastically with another train car of equal mass at rest, what would the speeds of the two cars be? So we have two trains now, two train cars. This one is coming in with a velocity and it collides with this one. This one has a velocity of 0. We can go ahead and subscript these. So 1 and 2. And then afterwards, what's going to happen after they collide with each other? So they're going to collide like this. Some stuff is going to happen. Okay, so we have some, crash there maybe. And then we don't know necessarily what's going to happen. Maybe this one is going this way, and maybe this one is now going this way. Something like that's going to happen, right? V2 prime and V1 prime. Or you could use initial and final and use like 1 as a subscript, meaning before the collision, and 2 as a subscript. All right, there's so many different notations you could use here. So we're going to use train car 1 has a velocity V1 without a prime initially. Train car 2 has a velocity V2 without a prime initially. And then after the collision, they have velocities with primes. Now, the important part for this part B here is that this is an elastic collision. Little bug landed on my head there. Elastic collisions conserve two things, not just the momentum, but also the kinetic energy. So an elastic collision means momentum, the total momentum is equal to the total initial momentum is equal to the total final momentum. So P total without a prime, or P total initial, is equal to P total prime, or P total final. So momentum is conserved. Momentum is always conserved in collisions. But since this is an elastic collision, we also have that the initial kinetic energy is equal to the final kinetic energy. Or again, we could think of this as, and let me just go ahead and use the same notation here. We could think of this as unprimed is equal to primed. So the kinetic energy initial is equal to the kinetic energy final. Kinetic energy before the collision is equal to the kinetic energy after the collision. So these are for elastic collisions. Only momentum is conserved for inelastic collisions. Because in an inelastic collision, when two objects stick together, what happens is there's some energy lost due to non-conservative forces. Okay, so since we have an elastic collision, there's a couple formulas that are useful for us, or rather there's one formula in particular that's going to be useful for us in addition to conservation of momentum, and that is the formula, let me put a comma here, it is V1 minus V2 is equal to minus V1 prime minus V2 prime. Let me just double check, just because I don't want to give you guys the wrong formula here. Just double check that I've got the
I think that's right.
got the
That's what
symbol.
I'm working out
It is?
too. Yeah.
Okay, good. Okay, so that second formula there with the V1s and the V1 primes, that formula comes from combining the momentum conservation equation and the kinetic energy conservation equation, and then canceling some terms on both sides. It's actually quite involved. Like you got to use a bunch of algebra to do it. But basically you can factor the kinetic energy equation because you have V squareds. So you can actually factor it into like a V minus V and a V plus V. And then you get some nice cancellation. And ultimately what ends up happening is you get this third equation here with just the velocities and no masses. It's a nice equation there. And basically the meaning of this equation, it actually has to do with something that came after this chapter. This is a statement about what happens to the velocity, the relative velocity, with regards to the center of momentum or center of mass. So that's really what the meaning of this equation is that the relative velocity between these two objects actually changes direction after the collision. Of course, the total momentum is still conserved, so the center of mass of that system still continues to move in the direction that it was initially traveling in. Okay, so that's enough of the review of the theory there. Let's actually answer this part B now. If the train car collided elastically with another train car of equal mass at rest, what would the speeds of the two cars be? I need some space, so I'm going to just delete all of this and we'll rewrite what we need here to solve this equation or solve this problem. So we have momentum conservation. The momentum initially is equal to the momentum finally after the collision. But only one car has momentum to begin with. So M1, V1, no prime, plus 0 for the second car because it's at rest. And they also all have equal mass, but we'll take care of that in a second. So M1 times V1 plus 0 equals 0, or excuse me, no, sorry. M1 V1 prime plus M2 V2 prime. Okay. Got a little ahead of myself. I was thinking of the next equation, trying to think ahead a little bit. But so since there's only the first car is moving initially, then the left side of the equation is just M1 V1. After the collision, both cars could be moving. We actually don't know their velocities, so we have two unknowns. Let's go ahead and keep track of that, because if we have two unknowns, then we need two equations, right? That's what makes elastic collisions a little bit harder than inelastic collisions, is because you have more unknowns, you need more equations. So these are unknown. Now we can use the equation which says V1 minus V2 is equal to minus V1 minus V2 with primes. And of course we know V2 is 0, so V1 is equal to minus V1 prime minus V2 prime. And we can just go ahead and distribute that minus sign just so we don't have to worry about it anymore. So it will come out as V2 prime as a positive and then minus V1 prime. It's nice to have the minus sign over here for this expression because it tells you that the relative velocity actually changes directions. So it's kind of nice to have the minus sign there. But when we're actually going through the problem and plugging in some numbers and stuff, then you kind of just want to get rid of that minus sign. Okay, now we can solve because again, we have two unknowns. So right here, these are our two unknowns. And those are the same two unknowns that we have in the above equation. And so it's two equations, two unknowns. All right, so now we can take the first equation and divide by M1. Let's go ahead and call this equation 1 and call this equation 2. And what I'm going to do is I'm going to, from here, equation 1, I'm just going to divide by M1. Just writing out all the steps here so it's clear exactly what we're doing here. And of course we have some cancellation here of M1s, leaving us with V1 prime plus M2 over M1 V2 prime. And now might be a good time to use the fact that these two objects have the same mass. If M1 and M2 are equal, then M2 and M1 will cancel, right? And they'll give us just a factor of 1 there. So now is a good time to cancel these two masses, but you don't have to. You can solve this problem even if the two train cars don't have the same mass, and that's actually a good exercise to go through. But we'll go ahead and say now M2 is equal to M1, and we'll cancel these masses as well, leaving us with the expression V1 prime plus V2 prime, or rather V1 is equal to V1 prime plus V2 prime. But from our second equation, From equation 2, we have that V1 is equal to V2 prime minus V1 prime. Well, that doesn't seem to necessarily make sense unless V1 prime is 0. So what we can do is we can set these two equations equal to each other. So set V1 equal to V1. Well, okay, so I should be careful about what I'm doing. So I should use this arrow because what I want to do is set equation 1 equals to equation 2. And so that means we have V1 equals V1 plus V2 with primes. And then that is equal to V2 prime minus V1 prime, like so. And then what I can do is I can actually, did I make a mistake there? V1 equals V1 prime plus V2 prime, and then V1 equals V2 prime minus V1 prime. Right, okay, yeah, that's right. And so I can take this equation now, this piece, let me actually highlight this piece. And I can subtract V2 prime from both sides. So we have V1 prime plus V2 prime is equal to V2 prime minus V1 prime. And what I'm going to do is I'm going to subtract V2 prime from both sides. And that implies that V1 prime is equal to negative V1 prime. But of course, the only way that V1 prime is equal to minus V1 prime is if V1 prime is 0. So V1 prime is equal to 0. Let's scroll it down a little bit. Okay, so if V1 prime is equal to 0, which by the way is a consequence of the fact that the masses are the same. If the masses were not the same, then that would not happen. So since V1 prime is 0, this implies that, let's take a look at equation 2. V1 is equal to V2 prime minus 0 because V1 prime is 0. Right, and so we can write it here in red maybe. V1 is equal to V2 prime. Which means that the second train car, after the first collides with it, the first one is at rest, and the second one is now moving with the same velocity that the first one was moving with. Okay, so that's the implication there. And that wouldn't be the case if the masses weren't the same. But that's definitely always going to be true when you have an elastic collision with two objects with identical masses. So two objects with identical masses will result in the two exchanging their velocities with each other. So, and that doesn't matter that the second the second train car was at rest. If the first train car was going 10 meters per second and the second train car was going 5 meters per second in the opposite direction, what would happen is just the two would exchange velocities. That always happens. And the reason that's the case, again, is because momentum is conserved. So the momentum of the center of mass has to continue on with the same momentum that it has before the collision. Okay. Any questions there about that part B? Part B really is a lot simpler than it looks here on the screen. We could really just jump. We could jump to the answer a lot quicker than this by simply recognizing that they have the same mass. And so when they collide elastically, they will switch velocities. You could even get to the answer mathematically quicker just by canceling the m's right away, right? We could just cancel these m's right away, and we'd have v1 equals v1 prime plus v2 prime, and then we would have this equation right here as well, and get to the answer a little bit faster, right?
Yeah, that's what I did.
Yeah, good. So that's what you want to do on the test too, right? You don't want to spend extra time. So if there's no questions, then we can do part C now. I'm going to go ahead and delete just that top part there. So part C, what about an inelastic collision where the two train cars stick together? So that's like this. So they come, this one comes in, and then they collide, and it looks like this, and then they're moving together now. So this is V1, this is V2, and there is only one velocity after the collision for an inelastic collision, right?
Yes.
So M1, so M1 V1 plus M2 V2 is equal to M1 plus M2 times V for an inelastic collision. And there's only one unknown here, only one velocity that's unknown, and that's the velocity after the collision. And just to remind you guys what I've written down here, this is the total momentum is equal to, the initial total momentum is equal to the final total momentum here. So I just wrote it down as M1 V1, right? All the masses again are the same, so we can cancel them. Oh, excuse me. I better be careful because this here is 2m, and it's that m there that cancels when they all have the same mass. And so what we're left with, and of course V2 here is also 0, so I forgot to make that term 0, right? So V2 is 0. What we're left with here is V1 is equal to twice V, which implies that V is equal to 1/2 V1. Okay. So half the velocity. So this one right here has half the velocity. So after the two trains collide, since they have the same mass, the system has twice as much mass. And so in order to conserve momentum, the velocity of that system with twice as much mass must have half as much velocity. And I think we actually did have a number. I'm kind of remembering the original statement of the problem here. We were given a number of 13 meters per second. So let's go ahead and clean up what we had before. So for part B, V2 prime would have been equal to 13 meters per second, right? And V1 prime, we already said, was equal to 0. Here for part C, we have that V would end up being equal to 13 over 2, which is 6.5 meters per second. And that completes that example there. So are there any questions about that one? Okay. So now I believe I'm actually out of examples. So I'm going to have to piece together some examples now. So I have the book, the ebook loaded up over here. So let me go ahead and bring that up. Let's take a look at maybe an example of an explosion, which is a kind of inelastic collision. So chapter 7, inelastic collisions. Give me 1 second here. Just want to make sure I find a good question. Okay, so I found a question here, so I'm going to go ahead and type this out. So it's a little bit quicker. And then we'll go ahead and make the color there black. An object at rest is suddenly broken apart into 2 fragments by an explosion. One fragment acquires twice the kinetic energy of the other. What is the ratio of their masses? Okay, this is question 10 in the textbook, in chapter 7, so in the problem section. So it's not an example problem, but this is an example of like an analytical type question, right? We're not looking for an answer in terms of numbers, but we're looking for like a formula for our answer, right? So an object at rest, what does it being at rest mean? Well, you guys tell me. You guys know what at rest is, right? What is the total initial momentum of this system?
0.
0, right? Because it's all at rest initially. So where does the energy come from? Well, there's an explosion, right? So that energy is going to come from, for example, chemical potential energy. All right, so one fragment acquires twice the kinetic energy of the other. What is the ratio of their masses? So the kinetic energy of one is equal to twice the kinetic energy, kinetic energy of 2. So object 1 has twice as much kinetic energy as object 2. And the total momentum of the system is 0. That means that the final momentum of the system must also be equal to 0 because momentum is conserved. Even in an explosion, momentum is still conserved. Okay. So we use prime to indicate final, right? So in that case, that means that the mass of object 1 times its v1 prime, its velocity, minus m2 v2 prime should be equal to 0, right? So that means that m1 v1 prime is equal to m2 v2 prime. Simple as that. Okay. How about let's work on the kinetic energy part a little bit now. So we have the momentum part there, but how about the kinetic energy part? So kinetic energy of object 1 is 1/2 m1 v1 prime squared, right? They have no kinetic energy before the collision or before the explosion. Now, after the explosion, they have some kinetic energy, right? So it's v1 prime squared here. That's got to be equal to 2 times 1/2 m2 times v2 prime squared. Okay. So we've written down the formula for the, we've used the momentum conservation and we've used the kinetic energy relationship here that was given to us. And so we should be able to cancel some stuff down now and figure out the ratio of the two masses. So that would be like m1 divided by m2, which is what we're after here. It says, what is the ratio of their masses? Whether you do m2 divided by m1 or m1 divided by m2, it doesn't matter much, right? It's just the reciprocal of the other. So what we have here is 1/2 m1 v1 prime squared is equal to m2 v2 prime squared, and m1 v1 prime is equal to m2 v2 prime. Okay, so that's what we have. So what we can do is use the fact that in this is the second equation here, second equation. So this is equation 2, this is equation 1. We can use this second equation to cancel out some terms in the first equation. Let me show you what I mean here. Excuse me. Let's break this equation up. So we have 1/2 m1 times v1 prime times v1 prime. So I'm breaking the square of v1 prime into v1 prime times v1 prime and grouping the terms kind of how I want them to be grouped. That's got to be equal to m2 v2 prime times v2 prime. Again, breaking down the square there. But now, these two terms in parentheses are identical. And so they will cancel. They're equal. So when I divide both sides of the equation by one of those terms, then I can cancel them out. I get 1, right? So those two terms cancel, leaving us with the following expression: v1 prime divided by 2 is equal to v2 prime. Okay, so this tells us the ratio of the velocities, right? So now I can take equation 2 and I can write it as m1 divided by m2 is equal to v2 prime divided by v1 prime, right? So m1 over m2 is v2 prime over v1 prime. And over here from this equation, we know that v2 prime divided by v1 prime is equal to 1/2. And so we know that the ratio of m1 to m2 is equal to 1/2. In other words, the particle or the object or the fragment that has half as much mass is going to end up moving twice as fast there. So M1 has half as much mass as M2, and it also has twice as much velocity. So M1 has half as much mass, twice as much velocity, and so it also has twice as much kinetic energy. So any questions about that little analytical example there?
No, I'm good. Oh, actually, um, is this something that we would expect to see on the exam or something?
It's fair for me to
Mhm.
ask you for an analytical answer.
Yeah.
Um, and so I would expect students to be able to kind of manipulate equations without having numbers. But I will, if I give a question like that, then I'll keep it contained, so it won't require like 10 steps to get through. Be something a little bit simpler, maybe like a couple steps, and that's it. So this
Okay.
one, this one is probably a little bit too advanced for the test. So this one took like several steps, right? So this kind
Yeah,
of question wouldn't be on there, but I could see a little bit of a simpler analytical question being on there.
more like the previous one, right? Because that one we could break down
Yeah,
pretty
yeah, yeah.
quickly. Okay.
Uh-huh. And if I do give those analytical questions, it'll be on the free response, so there will be like some extra space there for you guys
Okay. Okay,
to
thank you.
write your thoughts. Yeah. Mhm.
Yeah.
Okay, so we'll go ahead and go for another example. And let's go for something like center of mass. How does that sound? So we haven't done a center of mass from this chapter yet. Let's take a look at something that is something like this here. Question 50 in chapter 7. Find the center of mass of the 3-mass system shown in the figure relative to the 1 kilogram mass. So that means choose the 1 kilogram mass as your origin for your coordinate system. So let's go ahead and draw the figure here. Try and make it look nice and neat. So this, we have this here, we have a slightly larger mass here, and we have another mass here. We can go ahead and fill in these masses, or maybe we can like give them somewhat of their own identity here. Okay, so here's what I'll do. So I'll use the colors to write down the masses. So over here, so the green one is 1.1 kilogram. Pink one is 1 kilogram. That's where we're going to set the origin of our coordinate system. And then the black one here is 1.5 kilograms. Okay, so this is our coordinate system. These distances are given 0.5 meters and 0.25 meters. Okay, so this one is 1 kilogram. This one is 1.5 kilograms. The green one is 1.1. All right, so what do we do to find center of mass? Whenever we choose our coordinate system to be located at one of the masses, its distance from the origin is 0. So we can always ignore that term in our equation for the center of mass. So the center of mass is the sum over I of mi xi relative to our coordinate system divided by the sum of all the mi's, which is basically the total mass. So this is just the total mass. Okay, so sum up all those products and divide by the total mass, and that will give you the location of the center of mass relative to your coordinate system. So let's go ahead and jump into it then. Like I said, the first term is going to be 0 because it's right there at the origin, plus 1.5 kilograms times 0.5 meters, plus 1.1 kilograms. And then should I do 1.1 times 0.25 here?
0.75.
I should do 7.5 because the total distance from the origin is 0.75. Then we want to divide by the total mass, which is 1 plus 1.5 plus 1.1. And this is basically just a crunch the numbers on the calculator problem at this point, right? So just want to make sure we plug everything in correctly. So in your calculators, you probably want to write it like this: parentheses, parentheses, 1.5, 0.5. You actually don't need these parentheses. You can do 1.5 times 0.5 plus 1.1 times 0.75, right? And then close off your parentheses and then divide, but then open up a new set of parentheses because you're going to add some numbers now. 1 plus 1.5 plus 1.1. Then close off the parentheses, push the equal sign, and that will give you the correct answer there. One plus 1.5 plus 1.1, and we end up with 0.4. I'll just go ahead and round it, 0.44, and that would have units of meters because it is the x center of mass. On the right hand side we have kilograms times meters divided by kilograms. So that tells us that the location of the center of mass is somewhere right over here. Like it's not quite half a meter, which is where that the black ball is, but it's just before the black ball. That is our x center of mass, 0.44 meters. Okay, so let me just make a couple comments about that. Suppose that these three objects were, let's say, connected by some springs, okay? Or maybe these objects are planets and they're being gravitationally pulled on one another. Because we've found the location of the center of mass, we know that the momentum of that system whatever it has is always going to be the same unless it's acted upon by a net external force. So the location of that X center of mass, if it's not moving, it's never going to move unless there's an external force. Suppose these three objects are planets and there's gravitational forces of attraction between all three of those objects. The three objects might move around and change their positions, but the gravitational force is an interaction force between two objects. And so Newton's third law says that those two forces have to be equal and opposite. So pick any two pair of those planets and the net force cancels by Newton's third law. So all of the interaction pairs of forces between those three objects would cancel out. And so the planets themselves could move around and change their positions, but the location of the center of mass will stay the same no matter what. So for example, if this black mass here were to move to the left a little bit, then the pink and green mass would likely move to the right to compensate for the black mass moving to the left because momentum has to be conserved. Now, of course, in the case of planets, right, we need a Y center of mass location as well, right? Because planets would obviously be going in elliptical orbits around, like the sun or something like that, right? So just having a one-dimensional problem here is not quite good enough for like planets, but you could think of the same thing in terms of if these three masses were connected by springs, the same thing would be true. So they might be wiggling around a little bit, but the X center of mass would stay in the same location all the time. Okay, I think that is a good coverage of chapter 7. So the next thing that I'd like to do is actually just jump into chapter 8. Are you guys okay with that? I know we're a little bit over, but maybe we can do like maybe one or two examples for chapter 8. I'm sure chapter 8 is pretty fresh in your guys' minds, right?
Yeah.
Yeah, so Ju, you're also okay? We could go to chapter 8 now? Okay, cool. So we'll go to chapter 8. We'll try and do like two examples here. And I think that was a pretty good review session. I think this is definitely better than the first review, right? So hopefully you guys who are here will do really good. And then those of you who watch the video on YouTube, hopefully you do really good. I've just noticed over the years that a lot of students, like they say they want a review session, but then they don't show up for the review session. They do poorly on the test. So hopefully that's not you guys who actually are showed up. So chapter 8, rotational motion. And really, maybe this chapter should say rotational dynamics, because that's really what we're doing here. We're looking at torques and angular momentum, and so on. So really, maybe it should be called rotational dynamics. Let me go ahead and, since this material is really fresh in your guys' minds, let's just do like a quick little overview of kind of everything, and then we'll jump into some examples here. We'll just go straight to the back of the book and solve problems in the back of the book. Those ones are a little bit more challenging than some of the examples like in the textbook. Okay, so for rotational motion, we have quantities theta, omega, and alpha. And these are like x, v, and a. Okay, x, v, and a. So x is displacement, v is velocity, and a is acceleration. Theta is angular displacement, omega is angular velocity, and alpha is angular acceleration. And so theta is measured, for example, if we have a coordinate system where this is x and this is y, theta would be measured from the positive x-axis, standard stuff, right? We're used to that. Omega is defined as the change in angle divided by the amount of time at which that angle change took place. So this is really like velocity for an angle, right? So we call it angular velocity. So it's angular displacement divided by the time elapsed. And then alpha, when alpha is not zero, that's when omega is changing. So omega is changing. Then we have alpha is defined as the change in angular velocity divided by the time in which that change took place or the time elapsed. So exactly like v, the velocity, is change in x or displacement divided by the time elapsed, and acceleration is delta v divided by delta t, and the delta t there is the time that it took for that velocity to change. Now we have one more set of quantities which are kind of similar, and that's force and torque. Torque is kind of like a rotation. Oh, I wrote those in the wrong order. So torque, so let's put them right here. So we'll go ahead and switch up the colors too. So torque is like a rotational force. So a force that acts at a distance away from the center of mass of an object would cause it to start rotating, okay? And potentially translating as well. And then there's also angular momentum and linear momentum, and these are also very similar to one another. So if something has momentum, like for example, a ball on a string, that ball has momentum as it goes around in a circle. And so since it has momentum and it's moving around a circular path, it's going to have angular momentum because the angle is changing when something undergoes, like a circular motion, right? Okay, so those are like our key quantities here for this chapter. And these really need to be known. You need to know these for the test. You have to know these. You need to know their definitions and how they interplay with one another, right? So let's go ahead and just quickly remind ourselves, when acceleration is constant, we can write that the final position is equal to initial position plus initial velocity times time plus 1/2 acceleration times time squared, right? Well, we can do the same thing over here. And this will be the last time I draw an analogy here, and we'll just go ahead and move into some problems. We can write that the final angular, the final angle is equal to the initial angle plus the angular velocity initial times time plus 1/2 the angular acceleration times time squared. And here alpha is constant, and here a is constant. Okay, so that's the last analogy I'll draw for an equation there. Okay, let's go ahead and jump into some problems now. Or maybe you guys want to keep writing that down. I'll just go ahead and leave that there, and I'll go grab a problem. Okay, we'll take a look at question 14 in the back of the book here. So this isn't an example, but it's at the back of the chapter. A 61 centimeter diameter wheel accelerates uniformly. And I would say that this problem maybe is slightly more difficult than than a question I would ask on the exam. So this one has a couple moving parts here. There's quite a few steps to this problem. So this would be slightly harder than what I would ask on an exam. But certainly it's going to be good practice here. About its center from 120 RPM to 280 RPM in 4.0 seconds. A, determine its angular acceleration. B, the radial and tangential components of the linear acceleration. At the edge of the wheel after 2 seconds. Okay. So we basically have a wheel, and that wheel has an initial angular speed of, and let's go ahead and let's not say omega initial. Let's say omega RPM initial. Omega should really be measured in radians per second. So let's distinguish what we're saying here. So the initial angular speed is 120 RPM. And the final RPM is 280. Okay. And there's a delta t of 4 seconds here. And of course, we're going to assume that this acceleration is uniformly, right? It's a uniform acceleration. When it's a uniform angular acceleration, that doesn't mean that that doesn't necessarily mean that, for example, the centripetal acceleration would be constant. What that means is that the tangential component of the acceleration would be constant. So that actually doesn't say anything about the centripetal component, the radial component, which is what we're being asked here in part B. So the radial component will actually not be constant in this case. Okay, so let's go ahead and work on part A then. So for part A, we're going to apply the definition of alpha. Delta omega over delta t. The problem is we need to convert RPMs to radians per second. So that's the first thing we got to do. So 120 RPMs, 1 revolution is 2 pi, and 1 minute is 60 seconds. Okay. So 120 times 2 pi, and we see that the 120 and the 60 cancel, giving us a 2, and so omega initial is equal to 4 pi. And then we have omega final is going to be 280 times this factor of 2 pi over 60. Remember, you can always use this factor of 2 pi over 60 to convert from revolutions per minute to radians per second, right? So 2 pi radians is 1 revolution and 60 seconds for 1 minute. Now we have not as easy of a calculation here, but this comes out to cancel the zeros here, cancel the 6 with a 2, and that leaves us with a 3. So it ends up being like 28 pi over 3. If we want to keep that as an exact answer, we can. If we want to change that to maybe 9.3, and it is an ongoing 3 times pi, something like that, right? Let's just keep it as an exact fraction for now. Maybe it'll cancel if we work with it a little bit, right? So for alpha, now we're ready to do final minus initial. So 28 pi over 3 minus 4 pi. All of that is going to be over 4 seconds. And I could get a common denominator here. I could put this one over 3 and change it to a 12. And that would give me 16 over 3. So it would be 16 over 3 times pi and then divided by 4 seconds. And so that would be 16 over 12 pi. And the units here really should be radians per second. And of course, 16/12 reduces one more time to 4/3 pi radians per second. Of course, at any point there, you could have just punched it into the calculator and skipped all these steps of, common denominator and all that, and that's fine for the test, right? But this is the answer we get here, 4/3 pi radians. That is the answer to part A. So question B now. What is the radial and tangential components of the linear acceleration at the edge of the wheel after 2 seconds? The tangential acceleration is equal to r times alpha. Okay. We understand that because if this thing is accelerating by an amount alpha, right, then it's a distance r away from the center always. If it's undergoing a circular, if it's a wheel, right, it's a circle, right? And so since it's always at a fixed radius there, we get the tangential component, which is how the velocity, the tangential velocity of this thing, so pick a point right here, its velocity is like this, that's the tangential velocity, just to remind you. That tangential velocity is actually increasing as we go around, right? So over here, it might have been less, it might have been this much. Since it's accelerating, the velocity is increasing there, okay? So r times alpha is how we get that. So r here was 61 centimeters, so 0.61 meters times, oh, sorry, I made a mistake here. Yeah, I did make a mistake here with my units. It should be radians per second squared. The top has units of radians per second. These omegas are radians per second. And so our final answer for alpha should be radians per second squared there.
Also can you scroll up a little bit? I put down the diameter is 61 centimeters.
Oh yeah, it is also diameter, isn't it? Okay. Go ahead and fix that. So we'll put 0.61 meters over 2. Okay, so r times alpha, so diameter over 2 times alpha, 4/3 pi radians per second squared. And when we calculate this, so 0.61 over 2 times 4/3 times pi, we get roughly 1.28. Now it is meters per second squared. Meters per second squared. That is one part of part B. Since the angular acceleration is constant, again, the tangential acceleration will be constant because we're looking at a wheel. So the edge of the wheel, which is what we're interested in, right? It says at the edge of the wheel, right here. The tangential acceleration will be 1.28 meters per second squared. Now, at a point halfway from the center of the wheel to the edge, the tangential acceleration would be half as much. And the reason for that is because the tangential acceleration along the wheel is not the same everywhere. For example, at the very center of the wheel, the velocity of that particle in the middle, like if there's an atom in the center of the wheel, that atom isn't moving anywhere, right? So it has no acceleration. And so it makes sense that the further out along the wheel you go, the bigger the tangential acceleration has to be in order to keep the angular acceleration constant. Now, in order to get the radial component of the acceleration, we have to use our famous formula. The centripetal acceleration, which is the radial acceleration, is equal to v squared over r. Okay? And v is equal to r times omega. And so when we cancel out a factor of r, we get r times omega squared. Okay? R times omega squared. But the omega that we plug in is changing. Remember, this thing is accelerating. It has an angular acceleration, so omega is changing. That's why the problem tells us that we have to use some time information. We have to put in a certain value of omega after this thing has accelerated for 2 seconds. So omega is going to be equal to alpha times delta t plus, well, let's write it in the way we're used to seeing it actually. So omega final is equal to omega initial plus alpha t, right? So omega initial was the 120 RPMs or 4 pi radians. So 4 pi plus alpha came out to 1.28. And then we're being given a time of 2 seconds. So times 2 here. So let's go ahead and punch that into the calculator here. Right there. Oh, I have a random syntax error. That's why it was giving me trouble. Okay, so I come out with the answer 13.4 radians per second here. And this value here has to be squared. We take this value here, we square it, and we multiply by r. Again, we're looking at a point at the edge. So you plug in r is, what was it again? Half of 61 centimeters, right? So AC equals 0.61 over 2 times omega squared, 13.4 squared. Go ahead and calculate that real quick.
Professor, I keep getting 15.12 for my omega final.
15 point.
Well, maybe
12. Let's see, 4 pi is roughly, yeah, like 12.4-ish, 12.5. And then 1.28 times 2 is roughly 2.5. So comes out to like 15, yeah. Oh, I don't know how I got that. I had a syntax error there, so let me go run. I'll run through it one more time here. So 4 times pi plus 1.28 times 2. Yeah, 15.12. I'm not sure why that happened. I guess there was another mistake there.
No worries. I just checking my work too.
Okay, so let's get rid of that. So what did it come out to? 15.1 radians per second. There we go. Okay. All right, so let's back this up then. So 15.1. Okay, so 0.61 divide by 2 plus, or no, not plus, what am I doing? Times 15.1. Okay, 4.60. Is that what you got? This would be meters per second squared. Or 4.61 actually, if I round it properly. Is this what you guys get, or?
I'm, I'm getting a totally different number, but let me check my work again. I'm getting 69.73, which is
Wait a minute, yeah, what's going on here? Yeah, this is way too small because 15 squared is
yeah.
225.
I think your calculator is tired.
Actually, no, I forgot to square the 15, actually, is what happened there.
Yeah, that makes sense.
Yes, yeah, 69.5. Okay, yeah.
I thought,
I'm actually like starting to get very like worn out actually because we've been going for so long.
yeah,
Um,
I appreciated it. It's actually been super helpful.
that's good. Hopefully, the average is a bit higher. I'm not too worried
Mhm.
about this class. Well, this class, this class is always more frustrated with physics, but you guys did okay on the first test, like 50% average. And actually, after everybody dropped, I looked at the average earlier. Um, After like the people who didn't do so well dropped, the average is now like a 55% or something, right? So it's not too bad for a physics class. My other class, they they're like the calculus-based students in their second semester of physics, and they average like a 35 on the first test. They just took the second test, and the average was like 43. So improvement, but there's definitely some students in there who are not doing very well.
That's terrifying, actually.
Oh, you also got 69.5. Okay, good job. So we're all on the same page. Okay, so let's go ahead and jump into another one then, and we'll make this one be the last one. So let's get one that involves maybe some torque and angular momentum and moment of inertia, like all at the same time. Let's see if we can find one. You might have to pick like a hard problem actually just to get kind of a lot of those kind of in the same question, but let's see here. Oh, okay, this is a nice question actually. This is question 38. I might have put this one on the homework actually. I'm not sure. But maybe if it is on the homework and you guys see me solve it, then that'll be like helpful in some way. A small, oh, what? What did I do? I have no idea what happened. I can't even scroll over.
Can you exit
There
the text box? Yeah, yeah. There you go.
That was weird. Okay, so, right, let me drag this out. All right, a small, oh, I wanted to change that, so, okay. Black, there we go. A small 350 gram ball on the end of a thin light rod is rotated in a horizontal circle of radius 1.2 meters. Calculate, well, let's break it into parts here. So A, find the moment of inertia about the center of the circle. Remember that if you calculate moment of inertia about different points, you get different answers. So key point there from this chapter to take away. The moment of inertia is not unique, but the moment of inertia about the center of mass along one axis is a unique answer. The torque needed to keep the ball rotating at constant angular velocity if air resistance exerts a force of 0.02 newtons on the ball. Okay. I can add in a part C for us. So calculate the net, well, there's only one. Calculate the angular momentum of the ball, and D is the angular momentum conserved Oh, I worded that strangely. Okay, so here we go. We've got something from every part of this chapter here. So we'll go ahead and go through them one by one. Small 350 gram ball on the end of a thin light rod is rotated in a horizontal circle of radius 1.2 meters. Whenever you see something that says thin or light, really what they're saying is treat that thing as if it has no mass. So we're essentially just going to ignore the rod that the ball is on and assume that the moment of inertia is only due to the mass of the ball because the mass of the rod is so small compared. All right, so how do we do it? Well, if we have just a mass on the end of a rod, then the moment of inertia, where's my mouse at? Over here, okay, is going to be equal to the moment of inertia of a point mass in the book, which is mr squared. Okay, where r is the length of that rod. And so we get for this answer, this one is quick and easy, 0.35 times 1.2 squared. And we'll just crunch that on the calculator really quick. So 0.35 times 1.2 squared. And we get 0.504. Let's just round it off to 0.5. The units are kilograms times meters squared. Okay, kilograms times meters squared. Now, if this wasn't like let's say this wasn't a ball, but this was like an actual rod, right? It was, so the mass of the ball is really, that whole mass is actually spread across the entire rod. So what I'm saying is, instead of this situation, we have this situation. What changes? Well, we just use the formula for this situation here. It's rotating about the end point. So the moment of inertia for a rod rotated about its end point, if I remember correctly, is 1/3 mr squared. Right? It's 1/12 if it's from the center. If you rotate about the center, it's 1/3 if you rotate about the end. So you would just plug in the numbers like that and have a factor of 1/3. Okay, now the torque needed to keep the ball rotating at constant angular velocity if air resistance exerts a force of 0.02 newtons on the ball. If air resistance is exerting a force of 0.02 newtons on the ball, then that means it's also exerting a torque on the ball. So the torque due to the air resistance is equal to the force of friction. Let's use lowercase f, because we usually use lowercase f for friction. So it's the friction force times the radius. That friction force is going to be perpendicular to the radius there, from the center of the circle to the edge of the circle there, because the velocity is tangent to the circle. In other words, it's perpendicular to the radius. So there's no need to include like a sine theta here in this particular problem. Okay, so no sine theta. Let's go ahead and actually write it in anyways. Sine theta is just going to be 1 in this case, because theta is 90 degrees, sine of 90 is 1. And of course, if we need to exert a torque on the ball to keep it rotating at constant angular velocity, then the net torque on the ball should be 0. So this should be exactly equal to the torque that we exert. Okay, and so the torque that we exert should be equal and opposite to the torque that the friction force exerts. So 0.02 newtons times the radius of 1.2 meters. And this will have units of Newton meter. 0.024, or we should maybe change to scientific notation here. So the torque that we exert is going to be 24 times 10 to the minus 3 Newton meter. So that's a 24, not a 2.4. Maybe let's erase. It's kind of like a decimal. Okay, so that's the answer for part B there. Now, parts C and D are the parts that I added here. So these two right here are the ones that I added. They're not a part of the question if you look the question up in the back of the book. So calculate the angular momentum of the ball. Well, angular momentum is r times linear momentum. Okay. And that's when r and the momentum vector are perpendicular to each other. Well, since we have this case of rotating in a circle, then the radial vector and the momentum vector are going to be perpendicular. They're going to be at 90 degrees. So the sine theta that you might find here is going to be 1. Actually, I don't even know if the book talks about this formula. And momentum you can always write down as mass times velocity, right? And we can change the velocity to r times omega. So m times r squared times omega. And then really what we should do is we should recognize, but it actually doesn't matter in this case because we have a mass on the end of a thin light rod. This basically is a point mass, or at least we treat it as a point mass. In the case where you have other objects, like you have a rod or you have a sphere or you have a cylinder or something like that that's rotating, then what you should do is you should say I times omega. So angular momentum is I times omega. So let's calculate the angular momentum. We calculated I up here in the top right. And I actually, I did not give an angular velocity. Let's take the angular velocity to be 2 pi radians per second, so 1 revolution per second. Okay. So I should have added that in because I added the parts C and D, right? So I need to give a little bit more information. So for the angular momentum then, it's 0.5, and I think it was like 0.504 or something like that, times now 2 pi radians per second. And angular momentum has units of pi, approximately 3.14. Angular momentum has units of kilogram meters squared per second. Okay, kind of like momentum times a radius, right? Right here. So meters times kilogram meter per second. Okay, so there's the angular momentum. And now it's questions for you. Is the angular momentum conserved in the case of no air resistance? So if we're twirling this ball around on a string with constant angular velocity, and there's no air resistance, is angular momentum going to be conserved? What do you think about that for a second?
Yes.
The answer is yes. Good. For no air resistance. And then what about with air resistance and without the torque from part B? So remember in part B, we had to exert a torque to keep it rotating at constant angular velocity. So we're saying if we just have air resistance, is angular momentum going to be conserved?
No.
Good, so it will not be conserved. And then I guess we could add in one more part to that part D there. We could say, is angular momentum going to be conserved if there's air resistance and we're applying a constant torque to counterbalance the torque due to the air resistance? What would the answer be then? In that case, maybe we have to think a little bit harder. We have to remember that if the net torque is 0, then angular momentum is conserved.
What was the question you had asked again?
So if we allow for air resistance, but we apply the torque that's needed to keep the ball rotating at constant angular velocity in part B. So one way to think about the question and just get the answer right away is if we're applying the torque in part B, then that means we have constant angular velocity. And so if we have constant angular velocity, then momentum will be conserved. Because the angular momentum depends on I and omega remaining the same, right? So if omega doesn't change and I doesn't change, then we'll have conserved angular momentum. Does it make sense?
Yeah, I think so.
Okay. All right, so I think that's going to be it because we've been going for literally 4 hours.
It's been really helpful. Thank you so much for taking the time to work out
No
the
problem.
problems and everything.
No problem. There's one other thing actually I want to do because I said that we would cover some calculus stuff.
Mm.
So I want to actually go over just a tad bit of calculus kind of quickly.
That's only for the calculus-based students, right?
Right.
Okay,
But I'll just include it in this as well, I think.
okay. I think I'm gonna head out then. Thank you so much.
Okay. Yep. Okay, so now I'll just do like a quick bit of calculus that we'll need, and I'm just going to keep the recording going. So this is now calculus based, or in other words, 210 students only. And so I'm just going to go ahead and go through some of the things that they might need to know. First, since it's fresh on the top of our minds, let's go ahead and go through rotational motion. I think you'll see that even though there's calculus here, it's fairly straightforward. And that is simply that omega is normally written in this class as delta theta over delta t, and alpha is normally written as delta omega over delta t. Well, in calculus, what we do is we take the limit as delta t goes to 0 of this expression here. And what happens is that instead of deltas, we have the derivative with respect to time. So rate of change in terms of the derivative. And the same thing is true for alpha here. So if I take the limit as delta t goes to 0 of the definition of alpha here, then we end up with a derivative with respect to time of omega. And then using our knowledge of the antiderivative, or in other words, the integral, we can go backwards. So for example, suppose alpha of t is some function of time. Okay, so some function then we can find omega as the integral from, let's say, 0 up to some time of alpha of t dt And we have to add in the initial value, the value of omega at t equals 0. Maybe a better way to write it is actually this way here. So I'm going to go ahead and slide this over. I'm going to say minus omega at t equals 0. This is basically just the initial value for omega. So as an example, now I've shown something new here. Let's go ahead and do an example. Suppose alpha is equal to, let's say, 1/2 times t cubed. Okay. And let's go ahead and put units here. So 1/2 radians per t, t to the 5th. Oh, sorry, seconds to the 5th. This quantity has to have some bizarre units because we're going to multiply it by t cubed, which has units of seconds cubed. So that our final answer for alpha, if we were to plug in a time, would actually have units of radians per second squared. Okay, just a little small detail there, right? So if I wanted to find omega of t, and I know that omega initial equals 0, and I would do an integral from 0 up to t of this function 1/2 t cubed dt. And this is a straightforward power rule integration. So we would get 1/2 just comes out of the integral. We get 1/4 t to the power 4. We have to evaluate this expression at t and then subtract its value at 0. And what we end up with is 1/8 t to the 4th minus 0. So this is omega of t. And you guys can see, like, this is not terribly complicated, but it's a little bit more complicated than working with constant alpha, right? And so that's why we don't do this very often. Okay, well, now I have omega. If we scroll back up, I also have this relationship between omega and theta. So if I wanted to know theta now, theta as a function of t, then I could write theta is equal to the integral of omega of t dt. Let's say from 0 to t. And again, we'll suppose that theta initial, just like omega initial, we'll set theta initial to 0 just to see what happens here. So I would plug into my integral 0 to t, 1/8 t to the 4th dt. Integrating this expression again is just a power rule. The 1/8 pulls out of the integral. And then we end up with 1/5 t to the 5th. And again, we want to integrate this from 0 to t. And that's going to give us 1/40 t to the 5th power. And subtracting off at 0 gives us minus 0. So this function now tells us what theta is as a function of t. Okay, so we could now ask the question, how many revolutions? Let me go ahead and type this so it's quicker. So how many revolutions does this particle make in, let's say, 5 seconds? Okay, how would we figure that out? Well, we would understand that, of course, if the initial value for theta is 0, then the value of theta of t when t is equal to 5 seconds would be the total number of radians that this particle has gone through. Okay, so 1 over 4, 0, and then t to the fifth, so 5 to the fifth power is a very big number. Let's go ahead and calculate that. 1 over 40 times 5 raised to the fifth power. We end up with 78 point, let's go ahead and, it's 0.125, but we could really just round this off, right? And that is units of radians. This is the number of radians that this object has, this particle has gone through under its circular motion. But this doesn't answer the question how many revolutions. Now we have to convert radians to revolutions. And so we do that by dividing by 2 pi, right? There's 2 pi radians in 1 revolution. And so we'll take this, we'll divide by 2 times pi. We end up with 12.4 revolutions. So in 5 seconds, 12.4 revolutions. Okay. Another way to do this is the same way we kind of did it towards the beginning of the semester, where you might have a plot of, let's say, omega of t versus t here, and omega of t goes like this, and then here it's flat, and then it comes back down like this. And in this case, what you would do is you would calculate the area of this trapezoid right here. So the area would be equal to delta theta, right? Because delta theta is equal to omega times delta t. Whenever we have this omega times delta t type of thing, remember delta x is equal to v times delta t. When we plot v versus delta t, or v versus t, the displacement, the total displacement, is equal to the area under that curve. Okay, so one example of a question I might ask as a free response question, I might give everyone the same diagram here, okay, and I'd ask 205 students to do, area geometrically, okay, but I would ask 210 students to write, to find the area using calculus. Okay, so that would be like a fair game question there that I could ask both the trig-based and the calculus-based students. I could give them the same kind of setup, but I could ask 205 to just find the area, of those triangles and squares there, or rectangles, and then ask the 210 students to find the area, for example, of this portion right here using an integral, right? So you'd have to set up a linear expression here. So like right here, omega is going to be equal to some slope, right, times t. So that's linear in t. So when you integrate that, right, you're going to get something like 1/2 t squared, right? And the slope is still going to be there. Right, what's the slope what is the slope of this graph right here? Well, that's just the derivative, right? So slope is equal to the derivative of that function with respect to t. So you can calculate the slope by doing rise over run, right? Because it's a linear function there, right? But I might ask you to, so I might ask the 205 students, okay, what is the angular acceleration during that region? And they can do that by calculating with rise over run. But for 210 students, I might ask you to find that slope by taking the derivative of omega. Okay. All right, so that covers rotational motion. That covers rotational motion for the kind of calculus I might want you guys to use. Let's take a look at work and energy. And it's kind of the same thing here. It's kind of exactly the same, actually. So work is force times displacement. We could be a little bit better than that since we're calculus based now. We could say that work is an integral of the force vector dot product with the displacement vector. Okay. Now, in reality, this could simplify quite a great deal. It looks kind of scary. Like somebody who's just taken calculus 1, obviously this looks like a scary integral, right? But often what happens is that we forget about the vectors. We know the direction, right? We know the direction of the vectors. If they're in the same direction, it's f dx. If they're in the opposite direction, it's minus f dx, right? Simple as that. And I'll give you an example here. Suppose we have a constant force. So F is constant here. Well then, over a given displacement delta x, right? Then the area under the curve here is the work, right? It's an integral. So the area under the curve is the work. All right, well, what if we don't have a constant force? What if we have a force that looks like this, right? Suppose this is a circle here, a semicircle. Well, in this case, we would have to set up an integral, right? So in this case, again, the area, let's use the same color here, the area again, if we had a force like this, which kind of goes up to some maximum value and then kind of goes down back to 0 again, it would still be that the area is equal to the work. Okay. And I just chose this particular example here of a half circle because even if you don't know calculus, you can still calculate the area of a circle, right? You don't have to know how to set up that integral if you're in the trig-based class, right? The 205. But if you're in the 210 class, right, you should be able to set up an integral expression to calculate this area, right? And so probably what I would do if I were to give a question like this one is probably slightly too complicated, but here's one that isn't too complicated and would be fair game on the test, but I still think I'm not going to ask it. And that is to do a quarter circle. Quarter circle is a little bit easier to do because the equation for this quarter circle would be x squared plus y squared equals whatever the radius is squared. Right? Maybe we can set the radius equal to 1 here. So it's nice and easy. Then what you would do is you would solve for y, right? Y is going to be the square root of 1 minus x squared. and you take the positive square root because y values are positive here, right? And then you could get the area of this circle by setting up an integral. Square root of 1 minus x squared, like this, dx. And that would be equal to the work. Now, I wouldn't ask you to solve this integral. I would only ask you to set it up. The reason being is because if you integrate this from 0 to 1, you need techniques from Calculus 2. And I'm not going to assume that you guys are all enrolled in Calculus 2. But this would be a simple integral to do once you've got a little bit of Calc 2 under your belt. But you already know how to do this. You already know the answer for this integral because this is a quarter circle. 1/4 times the area of the circle. Area of a circle, pi r squared. R here is 1. So the answer to this integral is power of 4, right? Okay, so that covers work and energy. That's pretty much all there is to it there for the calculus in this chapter. Now, in the chapter 7, linear momentum, there is one example of calculus here. We have that force is delta P over delta T. And you guessed it, if we take the limit as delta T goes to 0, we have a derivative. And this is actually how Newton wrote Newton's second law when he wrote it down in the Principia, the book that he published that basically developed all of calculus. So this is Newton's second law right here as he wrote it. Okay, so dp dt. If the momentum is changing over time, then there must be a force. All right, so what do we do here? Well, we look at impulse. Impulse is delta P. So impulse is delta P. And delta P is F times delta T, right? So if impulse is F times delta T, then of course, if I have a constant force over time, then the area under this curve here is equal to the impulse, right? We can drop the vector sign here. We're working in one dimension. So the impulse is equal to the area there. This is force versus time, by the way. So F on this axis, T on this axis. Then of course we could have a situation again where the force varies. Maybe it varies linearly, or maybe it varies quadratically. It's like a t squared or something like that, right? You know, any number of things could be how it looks. It could do something like this, right? So force versus time. And again, it's the same thing. So 205 students calculate the area just from geometrical methods, areas of triangles and rectangles. And then for calculus for the 210 students, well, they would know that the force here is going to be equal to the slope of that line times t. And so they could do an integral to find the impulse. So delta p would be equal to the integral of f dt, not dx, f dt this time, not dx, from some value 0 up to, however many seconds, right? T seconds. However many it happens to be, right? So that's the calculus that you would need for chapter 7 there. And again, there are some shapes that we can put here where the area of that shape is pretty straightforward to calculate, right? Like a square, a triangle, maybe part of a circle, right? Something like that. Okay, how about chapter 8, calculus? By the way, this is the only calculus I expect you to know from chapter 7. There are some more things we could do, for example, with center of mass, but it's too complicated. It requires like 3 semesters of calculus, so we won't do that. Chapter 8, rotational motion. We kind of already covered a lot that's in here, but we should also recognize that we can do work with torque. So a torque exerted over an angular displacement will also do work. And so we can translate this to an integral of tau d theta. Okay, so I might ask you to calculate something like this, right? And so if there's some sort of torque, maybe it's a constant torque, and I'll ask you to, again, so torque, and here's theta, right? A constant torque would be like this. And so the area under the curve again is going to be the work. All of these principles in physics are kind of linked together, right? There's a lot of instances where we can just calculate like an area or like the slope of something, right? So there's area would be the work again. But if we had a non-constant torque, like maybe we had something like this, some sort of like staircase or something, well, I might ask you to, well, again, this is just simple rectangles again, right? So you could calculate the area here using rectangles, right? So maybe it's better to pick something that varies a little bit more. Just look at a square or something. So this is theta squared here, right? So if that's theta squared, then what do we do here? Well, the work, again, it's always the area. Area equals work. And so the work would be equal to the integral of theta squared d theta from some initial angle, maybe up to 2 pi or something like that, right? And so you'd have theta cubed over 3, and then you'd evaluate at 0 and 2 pi. So 2 pi cubed over 3 would be your answer for the work units of joules, right? All right, maybe I should let you copy that. So go ahead and copy that down. And then there's one last calculus bit here, just one. And again, you're going to see the similarity with the area idea. This is a really important idea in physics. That's why this idea is actually why we're able to teach physics to students without calculus, is this idea of having the area under the curve has a meaning, right? Or the slope of a curve has a physical meaning. That's why we're able to teach it to students who haven't even taken calculus yet, right? So it's a very powerful tool that simplifies things. So, and that last concept is torque. Torque is defined as change in angular momentum over change in time, right? The time elapsed. And so, of course, in the limit, the torque is the derivative of the angular momentum with respect to time. And so again, if I wanted to know the change in angular momentum, that would be torque times the change in time for the 205 students, right? So if there's a constant torque, again, it's area, right? So this is torque versus T. And the change in angular momentum is equal to the area. And if we were to do, with calculus here, maybe we do something like this. Maybe let's mix in 2 shapes here. So we have a rectangle and a triangle there, right? And so here, you'd have to set up an integral. You'd integrate the torque dt to get the change in angular momentum, right? And again, you could set up this integral and do the integral for a constant torque and do an integral for a torque which is proportional to minus t, right? The equation of this line right here might be a little bit, might add a little bit of a challenge to figure out the equation of that line, right? But if you know this point right here, and you know this point right here, right? You can figure out the equation of that line pretty easy. This is the x-intercept, so this is where y equals 0. That's the x-intercept, right? And up here at this point, right, you could use this point to figure out the slope, right? The slope is x2 minus x1 over y2 minus y1. And that's enough information, right? The x-intercept and the slope is enough information to plot the line. Or sorry, to write down the equation of the line. Right, and so that's the last concept there that requires calculus that I would expect you students to know how to do. But like I said, I will give everyone the same questions, but the students in 210, I will require them to show me that they know a little bit of that extra calculus knowledge. But if you're doing the calculus, but you stumble a little bit and you recognize, okay, I don't know the calculus perfectly, I'll still allow you to complete the problem without calculus, and I'll give you a good chunk of partial credit for that. So if you're able to just like write the integral down, but you can't remember, you forgot how to integrate that thing, then I'll still let you give the answer as like the area of the shape, right? But that won't get you full credit. That'll get you like a large portion of the points though. Okay, so that's all I have to say for the calculus students. So I just want to thank Ju for staying for the whole 4.5 hours there. So thank you, Ju. And this is where I'm going to end the review. Good luck on the exam. There is a test 2 practice assignment with a lot of problems from each of the chapters, but I chose problems that only require 5 minutes or less to solve. So that's a lot more similar to what will be on the test, questions that are maybe 5 minutes or less per question. So go ahead and go through that. Focus on the stuff that you feel like you're weak on, so that way you can improve your overall score for the test. Okay, don't work on stuff you already feel like you understand and then do poorly on everything else. Okay, so I'm going to stop the recording now.